Hi, everyone. Welcome to our second annual Robust Autonomy workshop that we're holding here at RSS on safe robot learning in the real world. My name is Andrea, and we're super excited to have everyone here. We have a great lineup of speakers, and let's just get into it. So for those of you who are joining us, these are all the workshop organizers, myself included. My name is Andrea. I'm a fifth-year PhD student at UC Berkeley. We're going to do a quick round of introductions just so everyone knows who we are. Feel free to direct message us if you have any questions. And let's start let's go down the list here. So Ransel, you can go next.
Yeah. Hi, everyone. I'm Ransel Senanaga. I'm a postdoc at Stanford.
Hello, everyone. I'm Somit Bansal. I'm a PhD student at UC Berkeley, and I will be joining as an assistant professor at University of Southern California in fall 2021.
Hey everyone, my name is Sylvia Herbert. I also finished as a PhD candidate at UC Berkeley, and I'm headed to University of San Diego in January.
Hey everybody, I'm David Prudovich Kyle. I also just finished up at UC Berkeley, and I'm going to UT Austin in 2021.
Hi everyone, I'm Jaime Fernandez-Fisak. I finished at UC Berkeley as well about a year ago now. I'm currently a research scientist at Waymo, and I'm actually about to start as an assistant professor at Princeton University in just a couple of weeks, on August 1st.
Awesome. So in this workshop, we have a lot of exciting talks, both from invited speakers and also from our contributed talks. But we wanted to get everyone sort of thinking about safety today. And the way that we're going to get everyone thinking there is we wanted to bring up these three main sort of questions or guiding thoughts that we had when we went into designing this workshop. And these three things are going to be addressed amongst a variety of talks that we're going to be seeing today. So the first thing to think about is, as autonomous system designers, how can we find and characterize failure modes in our autonomy that we're designing? The next thing we want to discuss is how can we learn from near misses? These are these moments when our system is almost about to fail. And that should be actually an indicator of what we can do better, not just the failures themselves. And the last thing is ultimately what we're really trying to strive for is figure out how we can generate autonomous behavior for which we can give meaningful assurances, both to users that are, ultimately going to be, for example, like just the public, or whether that be also like system designers like ourselves. Does anyone else have any other high-level comments to add to the guiding principles of this workshop? All right, great. So as I said, we have some fantastic invited speakers today that are going to give us some insights onto how to answer these questions. You can see them listed here. We have Katie, who's going to be going first, and then we have Tom and Ram in the morning, and then in the later part of the morning, we have Aaron and Tim. And Ransel is actually going to go through a little bit more about the schedule that we're going to have today, so people can calibrate sort of their attendance. But before that, we have some interesting statistics. Ransel, you want to take over?
Yeah. So last year when we started the workshop for the first time, so we had 11 contributed submissions, but this time the number has doubled. We have 22 submissions, and we have papers from all different areas, from perception to control. So some of the main topics this year include motion planning, AVs, game theory, optimization, OMDPs, and computer vision. And this is the schedule for today. We have the schedule in different time zones: Pacific time, Eastern time, Central European time, and Japan and Australia time. So we will start with 3 invited talks from Katie Dukes Campbell, Tom Dieterich, and Ram Vasudevan. Then we will have a short break and move to lightning talks. All lightning talks will be will start at 8:50 in Pacific time. So you have the chance to interact with all the contributed speakers. So for each talk, we will have 2 minutes question and answer session. So then we will again have a short break. Then we have 2 other invited talks, one from Team Barfoot and the other from Aaron Ames. Finally, we will conclude our workshop. So I hope you can see all this information when you join Feedloop or our website.
Yeah, thanks, Ranslo. A few other notes. So first of all, we're going to be recording this workshop. So that's what's happening right now in the background. Second of all, as Ranslo mentioned, we're going to have Q&A. We really hope that everyone participates. The way that we're going to run Q&A for both the invited talks as well as the lightning talks is primarily through the chat feature in Zoom, or you can also chat through the side chat bar in Feedloop. So if you're watching Zoom embedded inside of Feedloop, on the right hand side there's a chat bar. You can also put any questions there. If you're also participating through Zoom, you can alternatively just go into the direct chat box inside of Zoom. So please put any of your questions there for the speakers or for the invited talks, and we're going to be moderating those and then asking those questions to the speaker. So please feel free to engage like that. We'll also send you some reminders throughout the duration of the workshop about participation, but we hope that you guys sort of ask those hard-hitting questions to all of our speakers. Finally, I think if you have any further questions, again, feel free to direct message any of the organizers. We have the name organizer next to each of our names, and we can definitely help you out if you have any technical difficulties. With that, hopefully I haven't missed anything else, you guys. Are we all good to move on? All right, great. So with that, let's get on with the first speaker of our workshop. I want to introduce Katie Drace-Campbell. Katie is an assistant professor at the University of Illinois at Champaign-Urbana. Her research focuses on developing tools for autonomous robots that operate out in the real world with people. She draws from the fields of human-robot interaction, optimization, learning in AI, and control theory to do her research. With that, Katie, are you ready to give your talk?
Yeah. So hello, and sorry, I'm going to keep my video off just to make sure that things go relatively smoothly. But thank you for that introduction, and thanks for having me here. Today I'll be presenting work that was primarily done by my grad students, Peter Du and Tianchen Ji, as well as with collaborators from Stanford in Michael Kokendorfer's lab and Girish Chowdhury's lab here at Illinois. So as Andrea mentioned, I typically look at how to design safe autonomous systems, but today we'll be mixing it up a little bit, and we'll primarily be looking at how and where these systems fail, which hopefully we will come to the conclusion together that this is an important part of assessing safety and performance as well. So just a fair warning for all of the participants here. We will be looking at autonomous vehicle collisions. So if that is something that might bother you, maybe go take a quick coffee break for this talk. Okay. So when we talk about system robustness or failures in general, one thing that's important to remember is context. So different applications will call for different representations and different priorities. So in my group, we look at a range of different applications, ranging from things like agriculture to transportation and manufacturing. So within each of these different applications, one key thing that I would like to note is that we have some sort of increasing structure throughout these different applications. So if you'll allow me to make some sort of sweeping generalizations, if we look at things like manufacturing, we have a lot of control over environments, and the processes are really well defined. So safety is still very important, but the way you think about it is going to be very different. In transportation, we still have a fair amount of structure in that we have well-defined rules of the road, and we can clearly define what a collision is, or what a failure is, in that we typically want to avoid collisions. Nonetheless, we still sort of have some breakdown of the structure through some things like interactions with people, or when some of our assumptions are violated. And then finally, sort of on the other far end of this, this sort of poorly defined plot, we have things like field robotics or agricultural robotics, where we have an environment that is constantly changing. Something I actually learned since moving to Illinois is that you can actually hear corn growing. So it grows really fast, which makes things surprisingly difficult. Also, simple assumptions like GPS and localization and state estimation are not something I can really assume that is readily available. So often these sort of simple things fail. And finally, the way this robot will fail in this domain is often really hard to characterize. So it's not as easy as just saying this is a collision, much like in the transportation domain. So today we'll be talking primarily about the transportation domain here. And we'll be talking about our efforts in designing robust autonomous systems and how this relates to motivating validation techniques. So we'll spend most of our time talking about these 2 points here. And if there's time, we'll touch on some results in the agricultural domain. All right. Okay, so not too long ago, I was finishing up my postdoc at Stanford, where I was working on an autonomous driving project. So our goal was to develop a robust autonomous system that could safely operate in urban environments. So our autonomous vehicle was ultimately able to drive in a test facility that was a recreation of urban settings. But as I mentioned, today we'll be mostly talking about the failures, so we won't be looking at that end result, but basically what we learned along the way. So let's look at a few failure cases that we encountered. So here's a few early interventions that we had. So here's a video, my laser pointer. So here's our car we're driving here. We're going to be making a lane change once we overtake this vehicle. At some point, we will just sort of start careening back towards this vehicle here. And we need to intervene before a collision actually occurs. So this isn't a terrible failure, but this was an intervention case. And this, we believe, was caused by model mismatch. So the algorithms that we were running sort of underneath the hood were trying to achieve two goals. So one was efficiency, two was its navigation goal. So it was trying to turn right at some point in the near future. It thought it could execute this lane change, but the model that it was sort of running in simulation and trained on didn't match what was actually running on the vehicle. Here's another case. So this one's kind of a simpler one, but you'll see there are two bounding boxes here that keep sort of flickering in and out. We're trying to make it through this intersection, but we kind of hit this stall point here. So there's some confusion about whether or not there are different obstacles here, and it kind of just freezes. So while this isn't sort of an obvious failure in many ways, this is something that is basically caused by this interplane or mismatch between perception and decision making. And so these are relatively simple failure cases, but they were sort of important steps in helping us design our system in the end. And one of the ways we dealt with these sorts of failures was looking at robust decision making and control. So if we think about sort of the classical robust control problem, we typically formulate it as follows. So we have some system that we'd like to control. It's guided by some dynamics. We're trying to find our controller or our policy that can control this system effectively and hopefully safely, even though there are some disturbances or uncertainties in our world. So this is sort of a very traditional approach. This was sort of came about from the control community, and it was really sort of trying to take into account things like sensor noise and environment uncertainty. So not taking these sorts of uncertainties into account can lead to failures. So it can lead to things like state violations. So this is something that could relate to things like collisions, but can also lead to more classic problems like instability. So this is sort of the really most common sort of approach, and this is the widely studied problem from control. Another common concern is model mismatch. So this can be something as simple as maybe you have a simplified dynamics model and there's some things you're not capturing per se. But it can also be of interest to, say, the learning community. So in the learning community, you might be learning something in simulation or training some policy off some data, and then you have to make sure it transfers to your real system. You want to make sure that we have this sort of smooth transition. So here's a quick example here. So this is a naive imitation learning policy where we're trying to weave through obstacles. So this is our spoofed system here. And it's operating, and you'll see we have this sort of problem of cascading errors where we get sort of more and more egregious control. So we sort of have this unstable policy, and without having a more robust approach, we'll see that this is, again, sort of an unstable failure. And as I mentioned, a lot of the robust or adversarial learning community is looking at how to address both of these problems, but really addressing things like model mismatch. And the goal of these approaches are to make sure you maintain some performance. So this is a plot from some robust RL work. So in this case, you want to make sure you maintain some high rewards. So you're maintaining your performance despite changes in your environment or an increasingly adversarial environment. And this is sort of the end goal here. So you want to have this, stable and robust performance. And looking at these two different classes of failures can help address some of the interventions that we encountered before. So while I think these examples highlight some generally cool research efforts, but I think one thing to note is that they really highlight something that's important in the design process. So we had some failures we were able to identify, and then we can apply different research or engineering solutions to fix them. However, there are some sort of other failures that aren't really covered in these two examples. And while they might be related, these aren't really the failures that we typically think of when we think of an autonomous vehicle failing. So while these first two cases can help us sort of in the design process and design a baseline system that works, now we want to think about what are some of the other more complex failures and think about how those can also give us more insight to design, to our design. So one simple example in autonomous driving would be things like failures from interactions with other humans. And while we can take sort of human-robot interaction and cast it to sort of traditional robust control frameworks, and I'm sure many of the people here in this workshop will be talking about those sorts of failures, or how to design robust systems in the presence of those types of failures. We're going to explicitly be looking at how to find and identify these failures once we have a sort of baseline system that's more or less working. So again, now we want to turn this to a peer validation question and say, given that we have some autonomous systems, so it's post-development, how do we find meaningful failure cases that can help us assess safety and performance? Okay, so while finding failures might seem like a relatively easy problem, it's actually quite difficult. Especially in the autonomous driving domain. So we have this sort of interesting problem in autonomous driving where our high risk events or our collisions are often very low probability. So if we look at just the last two rows in this plot, this is for human driving. So if we look at the collision or fatality rate, we can see that we don't get too many collisions or fatalities. It's at a pretty low rate, so it's per 100 million kilometers driven. So you see that these sorts of failures for human driving are fairly few and far between. And this top number, it might be a little bit out of date now, but this is the disengagement rate. So this is the rate at which autonomous vehicles go from being driven in autonomous mode to the human safety driver in an unplanned fashion. So you can see that this rate is much higher than the human sort of counterparts. But if we're trying to show that our system is safer than humans, we need to get a lot of samples to both basically show that we are statistically significant in beating these numbers here. Okay. And if we were to think about actually deploying this and doing on-road tests to find these sorts of failures, it's basically going to be intractable and very inefficient. So we often need to turn to other solutions like simulation to help us find where these failure cases are. But even if we were to take just a pure sampling-based approach, we'll quickly find that we'll sort of be wasting a lot of computational power, and we won't exactly know where to search or what sorts of scenarios we need to set up. So let's walk through a simple example to sort of highlight some of the difficulties when setting this up and finding failures. So if we were to set up some simulation where we wanted to test our autonomous system, which again, we assume is fairly well designed. So we'll look at a simple case where we have an autonomous vehicle and say a pedestrian interacting. So if we had some model of this human behavior and we wanted to check for full coverage, we could discretize over the space and try and see sort of, given all of the different trajectories this pedestrian could take, are we sort of showing good performance or avoiding collisions? So for example, if we wanted to have a relatively simple human model, we could, again, discretize this and project it forward, and we can test in this simple case. We can also make this model more complicated and test a variety of different trajectories, and hopefully we'll find something sort of meaningful out of this. However, this might ignore possible but unlikely trajectories that could lead to a failure to something like this. And while this is sort of a crazy trajectory, it's hard to tell if this is something that is going to be useful or meaningful in our end test. But you can already see we have lots of different types of behaviors that we need to get good coverage over. And we already are sort of seeing this explosion in things we need to check for. And this just gets more complicated as we have a more complex scene and we start doing things like looking at other agents and start looking at basically all of the interplay that happens between these cases. So really what we want to do is we want to be able to find a method or use a method that can efficiently find disturbances or actions from the environments, like these different agents, that can lead to a failure. So hopefully instead of searching over all possible combinations and all different behaviors that could arise, we'll find something that's a little bit more direct. So to address some of these issues, we'll be using this technique called adaptive stress testing that was first presented by Richie Lee. And basically what this is going to do is this is going to cast the validation problem as a sequential decision-making problem. So instead of going for full coverage or a pure sampling-based approach, we just want to find a satisficing solution. So we're going to try and actively search our environment space for a likely failure. And so since we're casting this as a decision-making problem, we can now use tools like reinforcement learning. So you can see here we have this sort of typical pipeline that's common in reinforcement learning, where we have some simulator, and this is going to simulate our system that we'd like to find the failures in. So one of the sort of nice properties about this is a very general approach. And so now we have this simulator where we want to sort of query and try and find its failures. And this method will allow for different levels of transparency. So if you have a really simple simulator, you can find things like direct optimal solutions or model-based approaches. But if you have a really highly complex system, you can treat this as a black box and just control things like random seeds. So you can treat this environment actions ranging from different actions from different agents, disturbances in your environment, or just something that will control your simulator. The only requirement that you have out is some proxy or estimate of the likelihood of your actions and this event flag that tells you if a failure has occurred. So the key to making all of this work is a well-defined reward function, and this will help you guide your search through the simulation space. So at a very high level, basically what you want to do is you want to find the most likely sequence of events that will lead to a failure. So basically what we're going to do is penalize not finding a failure and applying unlikely actions. And we'll show some examples that will hopefully make this a little more clear. And one of the things that's really nice about this approach is that because most of this sort of tuning is done through this reward structure, it's very easy to hand off to other users. And part of the success of this approach and what allows it to be easily transferred to our industry sponsors is that this is a relatively intuitive formulation or way to think about searching a space. And you can easily add guiding heuristics or domain insights depending on sort of what you know about your system. Okay. So let's look at a quick example here. So here we have a agent here, and here, or our agent that we're trying to test. So we'll call this our system under test that has some dynamics and some other agents. So in this case, we'll consider pedestrians that might be poorly perceived. So we have some sensor module, but it might be noisy here. Okay, so in this case, we have these other participants, which are the other agents in this world. Okay, so our environment actions are basically the what we're going to be perturbing or trying to find failures in is in these participant dynamics, so we can control these other agents as well as the level of noise in our system here. And I am running low on time, but just as a quick note, since we are formulating this as a reinforcement learning problem, the solver that you use is going to be some variant of some RL policy optimizer. So this can be a neural network if you'd like, but we often like using Monte Carlo tree search because it gives you some level of transparency or some sort of interpretability, and it has some nice analogs to statistical model checking. And we'll skip through this. Okay, so as I mentioned, if you have just sort of a typical simulation or a traditional sampling-based approach, you'd get something like this. So you have sort of this nice behavior, and it's quite unlikely that you'd actually find collisions. Now, if we were to look at a pure adversarial example and case, one thing that we would find is that it's actually not that hard to find a failure when we have this sort of free moving pedestrian. So we would often get something that's like this, where we just sort of have this pedestrian that is a little bit suicidal. So we have these collisions that are not too hard to find now that we sort of allow a lot of freedom in where we search, but they aren't necessarily meaningful. And so by looking at this reward function and thinking about how we can find relevant failures, we can find things that are a little bit more meaningful where the car isn't necessarily at fault. So we can start sort of breaking down the different causes or different levels of uncertainty or where these were introduced to find different failures. And since I'm now officially over time, I'll show just two quick more videos. Here's another example of something that is really easier to find now that we have this sort of more multi-agent validation approach. So here's a simple example where we sort of have this mismatch in negotiation. And this is something that typical V&V tech tools have a really hard time finding. So again, since I'm low on time, I'll quickly just show some other failures for this ag domain, because one thing I would really like to hit home is that we talked a lot about these different techniques in robustness and validation, but they really only work because of the structure inherent in autonomous driving. So because we have rules of the road, we can design simulations, and we have these well-defined failures where we can do this sorts of searching method. But if we look at different domains, we often don't have this, so we have to sort of rethink about how we define robustness and how we find failures. I'll just show a quick video of the sort of failures that we typically see. in the ag domain, which are really hard to sort of break down and actually understand. So these are two sort of collision cases. And because of just how sort of uncertain and all of the sort of stuff going on in the environment, it's actually really hard to even specify what a failure is. Okay, so going back, I'd like to quickly thank my collaborators, and I'll take some questions.
Thank you, Katie. That was super interesting. I loved all the examples of failures. I feel like that's something that we should be seeing more in robotics and autonomous vehicles, seeing where things don't work. We have time for one quick question, I think. Let's start from the first question. So Hadass has a question for you about how can simulation cover error due to model mismatch and perception?
So this is a great question. So actually, this is one of the sort of really big challenges that we see is if you can't have a good model of something, then you can't really find a failure in that region. So when we were integrating the perception stack, actually coming up with a good error model for the types of failures you see in perception is really, really tricky. And I think that's actually one of the things that needs to be worked on more. But if I quickly go back to this case, so one of the, I guess the short answer is it's very hard and you can't necessarily. But if you now treat it as another disturbance, what you can do is you can treat this as a, basically one of your actions can be additions to, or noisy additions to your perception stack. So instead of achieving things like ground truth, you can have things like adversarial noise that's added to it. The basic idea is if you can be robust to very adversarial changes there, hopefully by sampling or perturbing this a fair amount, you can be robust to whatever happens in the real world. But one thing that's really tough is you don't necessarily have that guarantee.
All right, thank you. So we don't have time to get to all the questions. Katie, if you have extra time that you can spare, you can get into the chat box and maybe answer the questions for everyone to see sort of while the next talk gets set up. So now our next talk is from Tom. I think David's gonna set us up with that.
All right, let me try to spotlight you. Oh, perfect. Okay.
Okay.
All right, let me introduce you, Tom. So Tom Dietrich is the Emeritus Professor of Computer Science at Oregon State University, where this conference was supposed to be hosted before it went virtual. He's one of the founders of the field of machine learning and helped co-found the Journal of Machine Learning Research. Among his many research contributions are the invention of error-correcting output coding to multi-class classification, the formalization of the multi-instance problem, and the masked view framework for hierarchical reinforcement learning. So thanks, Tom.
Well, it's a great pleasure to get a chance to talk in this group. I've long thought that robotics is of that. So you'll see that there's some similarity in our presentations. So my plan for today is really to divide the presentation into two parts. The first is robustness in the small, I call it, and I'll focus primarily on how we could put some anomaly detection for runtime monitoring of deployed systems. The second half of the talk will be about robustness in the large, where I want to look at the larger, human high reliability organizations and what lessons we can learn from them for building AI and robotic systems. So there are lots of use cases in anomaly detection. Until maybe 10 years ago, there were very few people studying it. But the one I'm going to focus on is open category detection. And so the idea is that classifier has been trained on some collection, in this case, let's say, of obstacles that it might encounter in an autonomous vehicle. And I used to give the example of, well, suppose we trained an autonomous vehicle in North America, and it would know about deer and bicycles and tricycles and you know, basketballs and so on. But what does it do when we take it and deploy it in Australia? And I was just making up that example, but it turned out that that really happens with the Volvo's driverless cars. It turned out kangaroos moved in an unexpected way. Another closely related area that's studied in machine learning is out of distribution detection. So the idea here is that the classifier at test time is given an instance that was collected in a different way. For example, under different weather conditions, or with a different camera, or the camera just positioned in a different place on the vehicle, and so on. So in my lab, we've been looking at open category detection via anomaly detection. So the idea here is that we have trained an object recognizer on, say, K classes of objects, and but the test data may contain queries that correspond to additional classes. And so the plan is that given a new instance X, we run it through an anomaly detector, and it assigns it an anomaly score, A of X. And if that score exceeds some threshold, then we're going to reject the query, raise an alarm, and say there's something unknown here. If the anomaly score is small enough, then we'll just go ahead and classify. So there are a variety of technical approaches that have been studied in the area. There's density estimation, so you just try to build a probability distribution over all of the inputs X that you've seen, and then you can use the surprisal from information theory, the negative log of the probability. A problem with this is that it's vulnerable to what we call nuisance novelty, right? It turns out, especially in images, there are often new things happening in the background, but they're really not relevant to the task. And the other problem is that density estimation is a very hard problem, and one suspects that we're solving a problem that's harder than we need to solve. For non-parametric density estimation methods require exponential amounts of training data. There are methods based on distances, so finding the distance to the nearest training data point, and if that exceeds some threshold, you reject. There are methods that try to get around this problem of irrelevant features or nuisance novelty by taking the input and projecting it into sparse low-dimensional projections and calculating anomaly scores in each of those. And this helps to some extent to robustify against irrelevance and nuisance novelty, but it's it's a very indirect way of achieving that. And then of course you can take any of these sort of families and methods and make them more robust by using, say, Huberized type losses, other kinds of robust loss functions. So my master's student, Andrew Emmett, just defended his master's thesis a few weeks ago, and he did a big benchmarking study of many algorithms that exist particularly in the sort of data mining literature for anomaly detection with featureized data. This is probably less applicable in the robotic setting, but what we found was that after controlling for various other sources of variability, that using the k-nearest neighbor algorithm actually was our top performing anomaly detection algorithm overall. Although I need to emphasize that different data sets required different methods were good for different data sets. So it's the usual, annoying factor in machine learning that there is no one best approach. But if you're going to place your bets on something to start with, the k-nearest neighbor algorithm is a good choice. Of course, it's kind of expensive. There's a technique called the isolation forest that's almost as good and is much more efficient. But now, when we come to computer vision, we find that that our existing techniques really are not working very well. The challenge is that there are no good distance metrics. Certainly, measuring distances at the level of pixels is not particularly meaningful. And of course, images are very high dimension, and there's a high degree of nuisance novelty. And just as an example, one of the state-of-the-art methods for anomaly detection in computer vision when trained on faces from Celeb A, the famous celebrities database, and then asked whether house numbers from Street View house number database come from a different distribution, can't correctly make that decision. So that's how bad things are. So there are, again, a variety of approaches, and I'm not going to take time to review them all right now. Some of them are based on training a classifier and then extracting an anomaly score. Others are based on density estimation or trying to learn a distance metric in a latent space, autoencoders that find a good latent space, and so on. But it's a very active area of research. There were some papers just a few weeks ago at CVPR, and this week at ICML, there are several more. So, but we're far from having good performance. So let's come back to this question of open category detection and predicting with an anomaly detector. And let me talk about just the question of, okay, we need to decide, well, how are we going to set this threshold tau, for example, in order to detect, say, 95% of all of the out of open category queries, or maybe we want 99% of the open category queries. So a lot of work has been done in anomaly detection for the opposite case, which is to limit the false alarm rate. And so we just detect super obvious anomalies. Whereas I think in the safety critical side of things, we want to detect all, ideally, 99.99% or whatever, as Katie was pointing out, of those very rare cases. So how can we set tau in a way that can do that? Well, ideally, what we would like to know is the distribution of anomaly scores on these, what we call them the aliens, these open category queries. So we're going to, but it's unreasonable to assume that we have a labeled training set of such alien cases. We just saw how hard it is to find them. So what we'll assume is that we have a labeled data set of the known categories, and then a mixture, unlabeled mixture, that contains fraction alpha of aliens. And we're going to assume right now that we know alpha, which is an assumption that can be relaxed to some extent. And so our goal now is to detect with probability fraction 1 minus gamma of these open category queries. So if we had the cumulative distribution functions of everything, then it would be easy, right? If we had the CDF of the anomaly scores of the aliens, then we could just say, well, I want to set a target quantile of 0.05. I'll just find where that intersects this curve, and I'll get my threshold. But of course, we don't have a labeled sample, but one thing we can do is solve for the CDF of the anomalies by taking the CDF of the mixture minus 1 minus alpha times the CDF of the clean data divided by alpha. And so this would work in theory. In practice, things are a bit messier. When we plug in our estimators for estimated CDFs for here and here, then our estimated CDF for FA looks like this, right? So what we do is we take the very rightmost point where this curve crosses our target threshold. You can see it crossed it, I don't know, 8 or 9, 10 times, but take the rightmost point. And then we're able to prove a theorem that if we have n, which is a polynomial sample size, so that's O of 1 over epsilon squared and 1 over alpha squared, then we can get a PAC style guarantee that we will get an alien detection rate that will be at least 1 minus Q plus epsilon, where epsilon is our error term based on the size of our sample. So if we want a guarantee of 1 minus gamma, then what we have to do is we know n, we can choose how certain, how probably approximately correct we want to be, and we're assuming we know alpha, in which case you can solve for Q as gamma minus epsilon and plug that in, and you will get a theoretical guarantee. So it's kind of interesting to see that it is achievable. Of course, in practice, these kinds of guarantees are really loose. So on the left plot here, what we did was for some real data sets that you'll see in the next slide, we measured our actual error rate and then plugged in and based on that actual error rate, we asked, well, what does the theory say the sample size needs to be? And we compared that with the actual sample size, right? And if the theory had been exactly right, all these lines would lie on this diagonal. But you can see this is a log plot. We have between 2 and 4 orders of magnitude looseness in the sample size requirements. So that's typical for pack learning, that it gives you some sense of what's going on, but and it says guarantees are possible, but it doesn't, it's not really a useful guarantee. But it turns out the algorithm itself that uses the rightmost crossing of that estimate on several benchmark data sets gives reasonably decent recall here. This would be the fraction of anomalies that we're seeing. We wanted it to be 0.95. And so for some domains, it's not a problem. For others, you can think of the vertical gap here as the epsilon in the theory. So that's robustness in the small. I think anomaly detection methods are coming along, although I don't see how anomaly detection can get us to even 2 nines, let alone 5 or 6 nines of robustness and reliability. So my guess is that they're going to be most useful in cases where we're trying to detect them during testing, and perhaps in the adversarial testing case, that if we have difficulty characterizing in advance what an anomaly is, we could at least detect it in this statistical sense as well. But now I want to turn to robustness in the large. So some of you may be aware of this research that was done in the late 80s and the early 90s at Berkeley by folks in organizational studies. Todd Laporte, Gene Rocklin, Carlene Roberts were the founders, but it was a very influential line of research on what they called high reliability organizations. And what these folks did was to study organizations like air traffic control and aircraft carrier flight deck operations to try to understand why they were able to achieve extremely low error rates. And they found 5 properties that these organizations tended to all share. One was a fundamental preoccupation with failure, so a fundamental belief that the system has unobservable failure modes. And so they treat anomalies and near misses as symptoms of a problem with the system. In fact, if they've gone for a period of time without finding an anomaly, their assumption is they're not looking hard enough. The second thing is a reluctance to simplify interpretations. So when they see an anomaly, they want to comprehensively understand it, generate many hypotheses about what might cause it, and then in this in step 4, we'll talk about fixing it. A third thing is that there's a sub-team that is responsible for maintaining continuous situational awareness about the system. And this is where I think our dreams of self-driving cars probably are going to fail, because our human drivers cannot maintain that continuous situational awareness. A commitment to resilience is the idea that these teams practice responding to failure. So they practice improvisational problem solving. And finally, the idea of deference to expertise is that the person who might have the most expertise in a situation might not be the surgeon in the hospital, but the nurse. Might not be the director of the nuclear power plant, might be the janitor. And so the idea is that in a crisis, the final decision should be made by the person with the most expertise. And this line of thinking has had a big impact in aircraft cockpit. There's something called cockpit resource management that tries to help cockpit teams work well under failure conditions, and in the patient safety movement in hospitals. So I think HROs are inspiring to me because they give us a kind of roadmap for what it would take to make AI systems be high reliability organizations. So that we would need to maintain situational awareness, and that is something actually that AI methods are probably superhuman at doing, right? Because we can integrate hundreds or thousands of sensors if we have to, and maintain a probability distribution over the states of the system and the plant. Anomaly detection and near misses. Anomalies, yes, are studied a lot in machine learning. The idea of near misses is absent in the machine learning community, but I have a feeling it's much more present in the robotics community. So we have to pay more attention. And then generating candidate explanations for those anomalies and near misses. There's very little work on anomaly characterization or explanation, at least in the machine learning side of the world. And finally, improvising solutions. Improvisational problem solving is pretty much completely not studied in the parts of the world that I live in. One exception might be mixed initiative planning in human and AI planning systems. So if I were to give the AI community a report card on this, I would say that while we might be doing really well with situational awareness, we're flunking on two of the other things. And the last thing I wanted to think about is also about the question of designing a human plus AI team to be a high reliability organization. Because even very powerful AI, very smart AI systems will be surrounded by a human team. And so now let's go through these same four things. Situational awareness. The AI system can certainly track the physical aspects of awareness, but it needs to also establish a shared mental model with the human beings in the situation. And the human members of the team need to be aware of what version of the AI system they're using. Every time the software is updated, do they need to have a chance to understand what's happened? Anomaly detection, I think humans and AI need to work together to detect anomalies, and the AI system needs to detect when there's an anomaly in the human behavior, right? We see this particularly in after the analysis of crashes in aircraft, that the that teamwork was breaking down in the cockpit, and it would be really great if an AI system could detect that and perhaps take action. Generating candidate explanations, as I say, I think joint human-machine collaboration hasn't been looked at very much here. And improvisational problem solving, how could an AI system support a human team that's improvising in real time? So I think we're maybe not totally flunking on any of these, but we have a long way to go on these four characteristics. So in summary, I talked about robustness in the small, and the idea that we could use anomaly detection for open category detection. Our anomaly detection methods for featureized data are fairly mature, but for images and video and other kinds of signals data, it's rapidly improving, but we have a long way to go there. But as I said, I think anomaly detection by itself is not going to get us to 5 or 6 nines of accuracy. We need additional safety mechanisms. And then I talked about robustness in the large. Human organizations achieve robustness through a combination of situational awareness, anomaly detection, and improvisational repair. How can we build AI systems that can exhibit those same capabilities? So I will stop there and be happy to answer some questions. It looks like we have quite a few of them.
Hi, Tom. Thanks for a great talk. So I can quick ask a few questions that popped up in the chat.
Great.
All right. So the first one is from the first part of your talk. I think the question's basically trying to ask, how should we define the threshold? And since different people may have different tolerance for risk, is there sort of any guidance you might give?
Well, I think it would be a matter really of Q, the quantile you're trying to guarantee for.
Right.
So, and it depends a lot on the setting. So yes, that's what you'd vary, I guess. That's the short answer.
Okay. Okay. So the next
but
one.
But I should mention one thing, which is the whole idea of formulating the question of the probability of detecting an anomaly is already presumes that the anomalies have some well-defined probability distribution. And that decision, that concept itself is pretty dubious, especially in an adversarial setting. But perhaps it's reasonable in a sort of routine robotics setting.
So the next question is basically, how do we know when we should worry about tail events that we might be concerned about in sort of robust control adversarial settings, those kinds of things, versus when could we ignore them, especially given that these anomaly detection algorithms are unlikely to achieve, such perfect accuracy?
Well, I think anytime we deploy a system, we need to have some sort of monitoring in place, watching for anomalies. I think one of the lessons also of some of the undesirable side effects of deploying, for instance, bandit techniques in advertising or in recommendation systems has been there have been emergent behaviors of the broader system that were not anticipated by the designers. So I think whenever we deploy any kind of intelligent system, we need some kind of monitoring in place. Now, should the monitoring be active in the sense of actually intervening in the situation, or should it just be logging unusual events and near misses for some kind of a offline process to analyze? That seems like it would depend a lot on the application.
Thank you. And the last question we got on the chat is sort of also referring to the first section of the talk, but would a method that estimates alpha robustly in an independent manner be useful for increasing anomaly detection? Your slides seem to imply that it does not matter too much.
No, so there is a problem with estimating the fraction of anomalies in the mixture setting, is that alpha is actually not identifiable. So you can get a guaranteed underestimate of alpha, and there's a small but growing literature on that question. But unfortunately, our theory requires a guaranteed overestimate of alpha. And in our paper from ICML 2018, we showed that even small errors in overestimating alpha will lead to a lot more false alarms in the anomaly detection. So, so that's a big problem. But we do have, I would say, about 4 different algorithms that give reasonable estimates for alpha, which are of independent interest also, just in things like financial fraud, how many, but what is the background rate? So, great question.
Yeah. Well,
okay,
yeah.
well, thank you very much.
Thanks so much. Oh, we got one last one that showed up on the chat. If we have a few minutes, I think before the next one, so I can ask that. It says, following up on the previous questions about thresholds and distribution tails, you can argue that not all anomalies are created equal. I'm wondering about your thoughts on how we can or should combine the notion of probability of detection with the criticality of different anomalies.
Yes, I guess I've been assuming that we need to detect them first and then somehow characterize how threatening they are. But in Katie's talk, she in order to drive the simulation to kind of force the anomalies to occur, it sure would be nice if we had some characterization of them. It seems like an area where we need to think a lot more. Maybe in some cases we can pre-characterize them. In others, if they're really surprising, then we'll probably have to think quite a while about really what caused them and what we can do about them. So very, very, very nice. Okay.
Yeah. Well,
thank you all very much.
Yeah.
And thanks for these links in the chat. Wow.
All right, great. So with that, I would like to introduce our next speaker, Ram Vasudevan. So Ram Vasudevan is an assistant professor in mechanical engineering at the University of Michigan with an appointment in the University of Michigan's robotics program. His research focuses on the development and application of novel data-driven optimization and systems theory to quantify and improve human and robot interaction with one another and the environment. He's a recipient of an NSF Career Award and an ONR Young Investigator Award. So as a reminder, please feel free to continue asking your questions for Ram in the Zoom chat or the feed loop chat, and I will summarize them in the end. All right, with that, welcome, Ram.
Thanks. Hopefully everyone can see my slides. Yes. Okay, great. That's the hardest part. Thanks again for inviting me, and thanks for hosting this. I know it's really hard to do these virtually. I've tried to include, a link to a PDF of my talk down here. There's a bunch of videos in my talk. It's always really hard to get these videos working well. There's YouTube links in there, so just feel free to click on those when I play the video, and hopefully things will work out really nicely. So really great intro to my talk by Tom. I think the important message here is that, robust autonomy is really, really challenging. And the way that I like to think about it is sort of the best robust automators in the world are humans. We do a really good job. I don't know if we would call that autonomy if a human being is doing it, but you can look at driving, for instance, and we can look at driving over time, and you can compile statistics on the number of fatalities, for instance, in the United States. And it's a really good stat to take a look at. On the y-axis here are the number of fatalities per 100 million miles driven, and on the x-axis here are years, basically going up until I think 2013. And the numbers are amazing. Humans are really, really, really good at driving. It turns out this is driving across all of the United States, so that isn't just driving in sunny California, it's also driving in wintry Ann Arbor, Michigan. And in fact, all the way down here, we get down to 1 fatality per 100 million miles driven. It's an incredible statistic. Even at the worst case, when we didn't really have traffic rules, it was about 22 or 23 fatalities per 100 million miles. So still pretty damn good. And the really remarkable thing here is that, we've been driving autonomously, for a long time, for the past, I want to say maybe 10 years. This is a leader in our field, which is Waymo, doing incredible stuff. And the most that they've driven is 10 million miles. And, they've slowed down a little bit given the COVID crisis. But, this stat basically shows us that we have a really long way to go if we really want to say something serious about the safety of our systems, if we want to just do it by driving out in the real world. So the thing that really sort of gets me going is really thinking about how can we, focus on automation or verified automation, not just for self-driving cars, but for all of these different classes of systems. And can we start thinking about developing, a theory that could work well across these different systems? And again, because, doing these real world experiments is really expensive, and running simulations can only take us so far. The question for me is, how far can we take our math? How far can we take our theory? And in this talk, I'm going to really focus in on sort of the planning and control aspect. But you can imagine asking these same types of questions as Tom did in the previous talk on saying something about all of the systems that go into automating our real world robotic systems that we care about. I'm going to talk today about a technique that we've developed called reachability-based trajectory design, or RTD. I'll just show you a bunch of videos of it working across a bunch of different systems and give you sort of a general idea of how it works. So we'll start off by looking at this rover. This is in our lab, back when we had a lab. You're going to see on the top left the robot's view. You're going to see a camera on the robot on the bottom left. You're going to see a sort of a mock road and random obstacles. The obstacles are not known to the robot a priori. You're going to see a waypoint in black that is basically a high-level planner that's handing these waypoints off to a mid-level trajectory planner. There's going to be these obstacles. There's going to be the robot in blue. And then what we're going to do is generate a reachable set offline, and it's going to be control parameterized. And essentially, we're going to use that control parameterized reachable set online in order to do provably safe obstacle avoidance. And so you're going to see it now. And it's a little bit of a setup time, but you're going to start seeing it do fun stuff like doing lane change maneuvers and whatnot. This is really exciting, but in fact, we've actually been able to do quite a bit more. So this is from last year's RSS. We started getting this type of technique working with the University of Sydney on their campus, doing a full-on obstacle avoidance now with moving obstacles. And again, the reachable set here is on the left-hand side. Blue is the car, red are obstacle points. And essentially, we have this thing operating about 3 to 5 meters per second on this University of Sydney campus. The really cool thing about this technique is it hasn't just been restricted to sort of ground vehicles. We've actually been able to get it working on a variety of different systems. This is a quad rotor. And in this instance, we're generating, again, a reachable set. Now it's on the bottom right. You're going to see that. And it's doing obstacle avoidance and everything. Again, it's doing all of the planning online and using those reachable sets that is computed offline, online, in order to actually do obstacle avoidance. Now, the typical question most people ask when they see sort of these reachable sets is, well, how do you get them to work for really large systems? Totally great question. In fact, we've actually been able to do the same style of work on manipulators. And again, the same type of picture on the left-hand side is going to be true. Black are going to be these waypoints, which are configurations of the arm. And it's going to do online planning now, basically to avoid running into these shelves and basically to get to this goal over here. This is a 7-DOF arm. So it's basically I want to say a 14 or 16 dimensional state space model that we're actually doing safe online planning with respect to. In fact, the details of this thing we're presenting at this year's RSS. You can take a look at paper number 100, and in fact, you'll see behind this blue dot, you see it actually doing sort of dynamic obstacle avoidance. The really cool thing is that actually we've been able to get this working on a 40-dimensional robot. This is Cassie. Actually, in this case, we're doing the reachable set computation online, which has been a really remarkable development in our group. This is unpublished work, but the PhD student working on this just recently graduated, so hopefully we'll get this out the door in the next several months. So, we've actually been able to get this working on all of those different classes of systems. It's been really exciting. I'm going to talk to you at a pretty high level about how this method works, but first I'm going to describe some background and then go from there. So how does planning for these kinds of systems typically work? Well, for autonomous systems, usually planners are broken into 3 levels. The first is a high-level planner that does something like A star. The way that I like to describe it to my students is, it's something like Google Maps that's providing you some sort of turn-by-turn instructions. At the mid-level, we have a trajectory planner, and this is using some sort of simplified model of the vehicle usually, or a simplified model of the autonomous system. And what it's trying to do is essentially follow those turn-by-turn instructions as best as possible while maintaining some notion of safety. At the lowest level, we have a tracking controller, and this tracking controller is essentially trying to track or follow these trajectories that are generated by the mid-level planner. This tracking controller usually has to deal with all of the nastiness of a real system. So, there's a powertrain, all of these, series elastic actuators in a Cassie, and you have to be able to track those trajectories that are designed without any mind of dynamics, but still be able to say something about safety. And this is pretty difficult. Usually people think about introducing safety at various levels, usually these last 2 levels. Talk a little bit about the methods that have been applied to sort of think about safety at this tracking controller level. You can sort of think about them in 2 different classes. The first class is what I like to call check methods. What these methods try to do is essentially do collision checking for pre-computed trajectories, and a really popular method that's been applied across a variety of different systems. I think I saw Christian Peck actually on one of the participants on this call. You should chat with him. He's done some really beautiful work on applying these types of zonotope methods to essentially verify that a pre-computed trajectory can be applied safely. And actually, he has some really cool videos of showing this working in downtown Munich on a BMW. It's amazing. I wish we had a BMW that we could test some stuff out on. But Christian can describe all of the successes there that they've had. There's another class of methods, which I'll call correct methods. These try to do is essentially take a trajectory plan and take an associated control input and essentially try to modify that control input in order to ensure some version of safety. These methods have a really long history. So Ilya Kolmanovsky has a beautiful reference paper on reference governors that describes sort of a classical control theoretic sort of approach to thinking about these problems. Recently, they've sort of been elevated to another level using these control barrier function methods. Aaron Ames, who I think is talking later today, will probably speak beautifully about these methods. And then sort of the last class of these methods is what I'll call fast track, which Sylvia, David, Andrea, and Jamie can probably speak about beautifully. And again, these methods do a really nice job of essentially correcting the behavior of a motion planner in order to ensure some version of safety. I'm going to talk about introducing safety at a higher level, which is at the planning level rather than at the control level. And in fact, that's where RTD lives. And we call these types of methods, at least in our group, informally select methods, because they try to generate, they try to select not at fault or collision-free trajectories at runtime. The way that these methods work is basically, we're going to compute a reachable set, and it's going to incorporate trajectory-dependent error, and that's going to be done offline. And then online, we're basically going to describe how to describe or represent an obstacle in order to ensure that you can do real-time planning in a provably safe or provably not at fault way. So sort of the high-level description of where we're going. I'll talk a little bit about how RTD does this. So I'll think about this arm over here on the left-hand side. We'll have a set of trajectory parameters on the left-hand side. Those trajectory parameters are going to correspond to a particular motion of an arm, okay? And in fact, we're not going to focus just on a single trajectory parameter, but instead a continuum of them, and that's going to be represented, you know, using this left-hand side space of trajectory parameters, and on the right-hand side, a, you know, workspace representation of the effect of these trajectory parameters. And in fact, what's going to end up happening at runtime is that I'm going to have obstacles that appear. So this obstacle in red may appear. And in fact, what we're going to be able to do is map that obstacle into an unsafe set of trajectory parameters. Then at runtime, what's going to end up happening is that I may have some sort of configuration that's handed to me by some high-level planner that I want to get to. And so in fact, that may correspond to some location in my trajectory parameter space. And what I'm going to then do is write down this optimization problem in words, which is basically going to try to minimize some arbitrary cost function, which is a function of my trajectory parameters, such that I don't select a trajectory parameter that lives inside of this obstacle set. In fact, I'm going to do this in a receding horizon way. So I'm going to try to write this optimization problem and solve it repeatedly as I'm moving around in the world. Okay, and so that's sort of a high-level description of how this works. What I'm going to talk about now is sort of how this looks specifically in the case of cars. Again, if you're interested, we have a really nice paper on how this works in the ARM world on Thursday. But in the car world, you can sort of think about the problem as first starting off with this trajectory parameterization as us, you know, describing a differential equation for our system. And, you know, we have a set of trajectory parameters here that may correspond to a set of speeds and yaw rates and profiles of them over time. And in fact, what we're going to assume is that each speed and yaw rate profile or trajectory parameter essentially ends with a fail-safe maneuver. And this is how we're going to ensure that we can stay persistently feasible as we're operating our vehicle in the real world. So what that means in practice is that we come to a full stop. Okay, we're going to generate our trajectory over a finite time interval from 0 to TF, and we're going to ensure that it always comes to a stop over that time interval. Okay. Well, now, as we're operating our car in the real world, what's going to end up happening is that inevitably our low-level controller is basically going to introduce some sort of tracking error, and that's going to be depicted by this dotted blue line. And in fact, you know, we're not going to be concerned with just a single trajectory parameter, but instead a family of them. And in fact, that family of them is each going to correspond to a set of tracking errors that's going to be described in this bottom right in this picture, for instance. And what we're going to assume is that we have this function in green, which is something I'm going to call G, that basically bounds the effect of that tracking error over time. And what we're going to assume is that for each spatial coordinates, in this instance, we're working with a two-dimensional representation of the car, each spatial coordinate and each state of the vehicle corresponding to those spatial coordinates essentially has a bounding function, Gj, that is basically going to bound the effect of the tracking over time. Okay, so I'm going to assume the existence of this tracking controller. In fact, there's been several recent papers that have described how to develop or construct this tracking controller. One is by my group in this DSCC paper for quadrotors, where we describe how to actually construct this tracking controller, or how to construct this GJ function with a guarantee on its bounding behavior. There's actually been some work also by Murat Archak's group on developing sort of sums of squares ways of computing these tracking controller and associated tracking functions. I won't talk too much about how we actually generate them here, but if you're interested, do take a look at those two references. So what's going to end up happening is I'm essentially going to take my original dynamics F and add in this G, and actually I'm going to multiply that G by this disturbance function D, and D is essentially at each instance in time going to be drawn from -1 to 1. And in fact, the effect of this basically G's addition into my dynamics is essentially that I'm going to characterize all of the possible tracking errors that can arise by following this particular trajectory parameter. And in fact, what I want to be able to do then is essentially compute a forward reachable set for this entire dynamical system across all of these possible disturbance inputs into my system. And in order to do that, what we're going to do is apply sums of squares optimization. And I'll describe at a high level how this sums of scores optimization works. If you're interested in the details, please take a look at this IJR paper, which was just recently accepted. And the archive version is also available on our website. So what this sums of scores optimization is going to do is optimize over 3 functions, W, V, and Q. What W is going to do is it's going to converge to an indicator function on the forward reachable set. Importantly, it's a function of both the state and the trajectory parameters. We're going to then basically introduce these conditions on V. These conditions are actually going to look really similar to a Lyapunov type condition. In particular, V is basically going to behave like a Lyapunov function for the system, but I need to be able to introduce or incorporate the effect of the disturbance input, D. In order to do that, I'm going to use that function Q, and essentially Q is describing all of the possible behaviors of that disturbance input. And essentially by incorporating it in this way into these inequality constraints, I'm actually characterizing the effects of all possible D of T's over time. In fact, then, what you can show, if you take a look at the IJR paper, is that this W function is actually going to converge to an outer approximation. That is, its one super level set is going to be an outer approximation to the forward reachable set of the system. So in fact, what that means is if I can compute this object offline, well, then I have a function W that I can use online in order to actually ensure safety. What is that going to look like? Well, in fact, I'm going to take my obstacles over here on the right-hand side, and I'm going to map them over to unsafe trajectory parameters. And what that means is I'm going to be able to write down this particular optimization problem where I'm going to minimize some arbitrary cost function that is a function of my trajectory parameters, such that Wx of k is less than 1 for all x's inside of the obstacle. Okay? And so that's going to be the optimization problem that I'm going to try to solve online. The problem, however, is that that obstacle is going to correspond to a set, right? And it's going to have some volume to it. And I want to be able to ensure safety across that entire volume. And so in practice, these two sets may not be convex. And so doing some sort of intersection is going to be potentially very expensive, especially if I want to do real-time planning. So one way that you could think about solving this problem is by discretizing that obstacle into a set of points. Now, that's a problem for us. And let's talk about why. So this is my unsafe obstacle over here. I have my unsafe trajectory parameters on the left-hand side. I could discretize my obstacle's boundaries by just selecting a set of points. Well, if I did that, it would correspond to an inner approximation of the set of unsafe trajectory parameters on the left-hand side. So what that means in practice is that if I just ensured safety by looking at these discretized obstacle points on the right-hand side, I actually wouldn't be guaranteeing the safety of the trajectory parameters that I chose. So in fact, what my students were able to do was actually show that there's a strategy to overcome this by essentially buffering the obstacle by some buffer B, and essentially selecting points on that buffered obstacle in a pre-specified way. And if you did that, you could essentially generate an outer approximation to the set of unsafe trajectory parameters. And in fact, in this paper, they describe a way to do this for arbitrary convex vehicle forms. Okay? The obstacle here does not have to be convex, it's just the vehicle that does. But in fact, I'll show you what this looks like in the case of a rectangular car. So suppose I have my rectangular car, suppose it has a width W. Suppose I buffer, and my buffer is chosen as some buffering distance between 0 and 1/2 the width of my vehicle. Well then, if I discretize the points on the obstacle and make sure that the point spacing between those is less than or equal to 2b, well in fact then you can prove that you won't actually run into the obstacle as long as you ensure that you don't intersect, or the forward reachable set doesn't intersect with these discretized obstacle points. Okay, that is, the discretized obstacle points here are generating an outer approximation to the set of unsafe trajectory parameters. And in fact, that's really great because this is a constraint that I can write down in my optimization problem. And in fact, because this is a set of points, it's actually something that's really easy for me to write down and be able to use at runtime. So as I mentioned, we're really sort of big on trying to evaluate this across a bunch of different systems. We've done quite a bit of work on this. I'll show one example sort of in a little more detail before driving into sort of a bunch of different examples. So the first example I'll talk about is a turtlebot. So we can look at a high fidelity model. So this sort of looks like a Dubin's car with dynamics system. And I can have a planning model that's going to look like this. And again, there's going to be some tracking error associated with using these trajectory parameters to track, or this control input to track some trajectory that is generated by this planning model. But we can build bounding functions, we can do all of the work associated with computing a forward reachable set. And then what we decided to do was actually apply it in the real world, in the simulated world here. And essentially what you're seeing here is our simulated world doing basically planning in real time, avoiding a set of obstacles. And what we wanted to do is evaluate, if this reachability-based trajectory design ran into any obstacles first. And second, if it actually was able to get to a goal. Now look, we're computing these forward reachable sets. They're outer approximations. We're generating a set of unsafe trajectory parameters. We're doing it using outer approximations. So are we being so conservative here that we're not somehow allowing ourselves to be able to robustly do planning? So that was the thing that we were also very concerned about. So we've done a bunch of different evaluations. The first one I'll show is in the simulated environment. We generated sort of 10,000 different scenarios. They're totally random. And we compared a bunch of different planners, RTD, an RRT-based method, and a nonlinear model predictive control-based method. You can find the details down here in this IGR paper, but again, we tried to be really exhaustive here and make sure that we were giving RRT and NMPC as much flexibility as they could, while using sort of state-of-the-art methods that we could find in the literature. The takeaway message here is that we get to a lot of goals, so we're not that more conservative than the other methods, and importantly, we avoid crashes while doing this. Okay, so this is one example. The next thing we wanted to do was show that we could apply this on a realistic car model. And so we did this using a car sim model. This was given to us by our collaborators from Ford. So it is actually a model of a Ford Fusion, and I'll skip ahead here. And what you're gonna see is essentially us running it in car sim. The track here is actually the M-City track here at the University of Michigan. And so the speed limit here is restricted to, I think, being less than 60 kph, but you're gonna see it actually go around this track. And you can see what the planner is thinking on the right-hand side. The really cool thing is, again, since it's doing receding horizon control, it basically is making its decisions only when it's actually seeing the obstacles. And so it does have a finite sensor width that it's actually using while doing planning. And to sort of see that, I'll jump here to the end, and you're gonna see sort of a roadblock here. And essentially, the vehicle is not going to be able to see this roadblock until it gets close by. In fact, it's going to think that it can do a lane change here because it doesn't see the obstacle behind this yet. So it does this lane change, and then it realizes that it can't actually make it past this roadblock, and it comes safely to a stop. As I mentioned, we've actually extended this to moving obstacles. It turns out that V function in the optimization problem allows us to construct a time varying forward reachable set. The problem with moving obstacles is that they can run into you even if you're parked. I don't know if anyone's ever had that experience of having their car parked and then someone runs into it. Now look, you can't always ensure the safety in arbitrary scenarios of autonomous systems in the real world because there's malicious actors. So in this work from RSS 2020, what we showed is this novel notion of safety that we called non at fault, where basically our car is not at fault if it comes to a complete stop and gives the others around it time to come to a break. And in fact, we did an evaluation of our system. You can see it in simulation up here on the top right, but I showed you a video of it actually using this EV platform on the left at the University of Sydney. And the green sets here are actually time varying forward reachable sets. Again, we did a fairly exhaustive evaluation of this. You can find the details in that RSS paper from last year. But we compared it to a state lattice approach. And again, you can see that we reach more goals. So we're not that much, we're not conservative. We get to the goals quickly, and we actually have a higher average speed, which is really cool. We've actually done this on a bunch of different scenarios, like unprotected lefts. And so you're going to see what this looks like on the top left here. And in fact, the vehicle sort of waits until it knows that it can go around these obstacles. I should mention in this instance, it's actually assuming that it's handed a conservative prediction of the surrounding road users. It's an important assumption. That's having a computer vision system that's able to reliably hand you these types of things is really important to being able to say something about safety. The last thing I'll mention is we've done a bunch of different comparisons. I'll sort of list them all out here. Ooh. I'm jumping too far ahead. Okay, here we go. You can find all the details here, but we've tried really hard to make all of this as accessible and as useful as possible. I'll put some links of the code base that you can use to rerun these numbers and regenerate everything. Again, we've done it across a bunch of different systems. I should add a table line here for Cassie, but we haven't written that paper yet. And I'll end sort of by thanking all the people who've actually done the really hard work here. A special shout out to Shreyas, whose slides I have used quite a bit of. Again, our sponsors, Ford, NSF, and ONR. The code here is down at the bottom. Takeaways again. So RTD enables collision-free or not at fault planning. Check out our paper on Thursday, which describes how to do sort of reachable set computations in a nice way for manipulators. And again, the link to all the code that we've described for this talk can be found on the left here, or on the right here. That's all.
All right, thank you so much, Ram.
Mm-hmm.
So you got several questions in the chat, and I think we only have time for maybe a quick one, but if you'd be willing to take a look in the chat afterwards, I think
sure, definitely.
How about, this one was interesting. I was wondering how you bound the set of disturbances you'd like to consider for your robot. Since you may encounter unseen disturbances during operation, are you able to scale these sets online?
Yeah, so that's a really good question. In fact, our more recent work is looking at trying to develop techniques that can scale or incorporate sort of information about the world at this particular instance into our model. So if you look at the ARM planning work, for instance, one of the things we've done is like develop a sort of forward reachable set parameterization that is not just a function of some trajectory parameters that are basically describing the behavior of the system that you'd like to see, but also somehow trajectory parameters that are a function of your current state. And so what that means in practice is that, for instance, like if I know my velocity looks like this in one of my joints at this instance in time, I can essentially treat that as a trajectory parameter that I'm not allowed to choose at runtime, but is essentially something I have to nail down right now. And so as a result, you can make your forward reachable set, richer, right?
Okay, great, thank you. So as I mentioned, there's more in the chat, but for now, we're going to go ahead and have a break for about 20 minutes. So we're gonna start 10 before the hour. All right, great. Thank you so much, everyone.
Thanks.
All right. Hi, everyone. Welcome back. So in the next section of our workshop, we're going to be going through our contributed talks. So the way that this is going to work is we're going to have these pre-recorded 3-minute talks. And these pre-recorded 3-minute talks will then be followed by a live 2-minute Q&A session with the authors of each of the papers. So please just follow along, watch the videos, and then afterwards you can ask any of your questions in the Zoom chat box. We'll be monitoring them, and you can ask these questions to the authors live for them to answer. So with that, let's get started. We're gonna watch the first talk by Frank here.
This video presents our paper titled Encoding Defensive Driving with Non-Cooperative Differential Games. Safe and efficient control for autonomous navigation requires interactive decision-making. Often, it is natural to express this interactive decision-making problem via a multiplayer differential game. For example, vehicles approaching an intersection engage in such a game. Game theoretic control strategies typically encode safety, either adversarially despite worst-case circumstances, or probabilistically across some distribution. Here, we introduce a different notion of safety based on an adversarial time horizon by partitioning the time horizon into adversarial and cooperative components. Our approach is reminiscent of most adversarial frameworks in its basis in non-cooperative game theory, but is distinct in its use of non-zero-sum formulations. This allows our framework to be applied to scenarios with an arbitrary number of agents. Consider an ego agent who imagines that other agents will briefly engage in unsafe behavior, for instance, due to temporary distraction. The ego may respond by behaving more defensively during this period of time. To model this, we split the total time interval into 2 subintervals, adversarial and cooperative phases. To encode the ego's defensive tendency, we encourage adversarial behavior for non-ego agents by assigning each a distinct running cost for each phase, GADV and GCOOP for the adversarial and cooperative phases, respectively. We also introduce constraints by adding barrier functions as cost objectives. Our examples involve autonomous agents with 6 states that evolve according to augmented bicycle dynamics, with interaxle distance Li for each player I. Each agent controls jerk and front wheel rate, which are aggregated to form UI. For all agents, cost functions are defined to penalize input effort, deviations from reference speeds, and deviations from lane centers. Additional costs are defined for non-ego agents to encourage collisions during the adversarial phase and discourage collisions afterwards. All vehicles are constrained to stay within their lanes and within a range of speeds. The ego agent is additionally constrained to stay sufficiently far away from other vehicles. Our first example concerns two vehicles heading towards each other on the same road. The ego and oncoming vehicles' trajectories are in red and blue, respectively. Large dots indicate initial positions, while smaller dots indicate 3-second trajectory snapshots. The ego imagines the other vehicle curving towards it to cause a collision and thus swerves away to stay safe. This swerving becomes more extreme as we increase the adversarial phase length. Next, consider a merging example with 6 vehicles. As the adversarial phase lengthens, P6 speeds up and swerves rightwards, attempting to collide with P1. Meanwhile, P2 and P4 slow down to more quickly approach P1. To summarize, this paper presents a novel formulation of safety inspired by defensive driving in which we explicitly encode robustness in the adversarial phase of a non-cooperative game. Our results confirm that longer adversarial phases result in more extreme evasive maneuvers. Thank you for your interest in this work.
Okay, great. Thank you. Frank, are you there?
Yeah, I'm. Can you hear me?
Yes, we can hear you.
Okay,
great.
cool. I just managed to allow my camera to stream. So, yeah, I don't know if people can see me, but
Yeah, we can see you. Great.
okay, cool.
So, how should a system designer select a suitable T adversarial? Should it be chosen heuristically, or is there any idea about a principled way of computing this time?
So far, it's heuristically. We do it by a case by case basis, and we're currently looking into ways to make it more systematic. There was also an interesting suggestion a while back about how each player should have distinct adversarial phase times. So currently, right now, we set all the players to have the same adversarial time length, but something more ideal could be to have each player have its own adversarial time. So potentially, players who are sort of farther away from the ego vehicle or agent don't have to be modeled quite as adversarially. And similarly, for other agents who are not behaving as irrationally, and so having this sort of flexibility would sort of really highlight the strengths of some of this algorithm or this approach, in our opinion. So as of right now, just a TLDR, there's no formal method for sort of generating these adversarial times. It's kind of heuristically and just whatever makes the experiments work the best.
Okay, great. Thank you so much, Frank.
Yeah, no worries.
Hello, my name is Luke, and I'll be talking about our recent work on incorporating robustness to uncertainty in the terrain into trajectory optimization for robot locomotion. Incorporating robustness to terrain uncertainty into motion planning could greatly benefit the development of safe, legged locomotion strategies for robots. As Spot demonstrates in this video, unmodeled disturbances from the terrain, such as abrupt changes in friction due to banana peels, can cause robots to slip and fall. And while Spot can eventually get back up, a more robust strategy would have been to avoid the banana peels altogether. One common method for planning robot motion over terrain is called contact implicit trajectory optimization. In this method, contact with the terrain is modeled through complementarity constraints on the states and the ground reaction forces in an optimal control problem. However, these complementarity constraints represent a precise model of the terrain, and as a result, the solutions are sensitive to errors and uncertainty arising from the terrain. Our work here focuses on including uncertainty in the terrain model. Specifically, we model uncertainty in the friction coefficient and in the distance to the terrain using normal distributions, and we replace the complementarity constraints with an expected residual cost, where psi here is a residual function that in the absence of uncertainty models the complementarity constraint. As an example, here we eliminate the constraint on the normal distance and add an expected residual cost on the normal distance and normal force. We've tested our robust approach in two examples. In the first example, shown on the left, we tested friction uncertainty in a problem involving sliding a block. Including the robust cost term shortened the sliding duration and increased the sliding velocity, as well as increased the control effort compared to the standard contact implicit approach. Moreover, when we simulated these controls forward and perturbed the terrain friction, we found that the robust controls produced less variation in the final position. In our second example, we tested uncertainty in contact distance in a constrained hopping example, where this hopper can only move horizontally and only via contact with the ground. In this case, including the robust cost, which is shown by the orange example, produces more foot clearance than the standard approach. Moving forward, we plan to test our approach in examples with more complex locomotion dynamics. In some of our preliminary results, in which we've included both the friction and distance uncertainties, the robust cost produces a higher jump, shown here by the orange trajectory. Combined with our previous results, we believe that our robust cost biases towards solutions that avoid contact with the uncertain terrain. In our work, we've shown that incorporating uncertainty can be useful for generating terrain robust trajectories. Moreover, we believe that future work could fuse our method with online estimation methods to update the terrain model from locomotion data. This would enable us to change the uncertainty and therefore the robustness online, leading to safe and adaptable locomotion strategies. And with that, I thank you for listening.
Thank you, Luke, for the great talk. You there?
Yes.
I have one very quick question. So do you also incorporate any dynamics uncertainty right now in your framework? If not, can you comment on how that changes your framework if you want to incorporate those uncertainties?
Right, so right now we're focusing solely on incorporating uncertainty from the terrain because of the difficulty in including uncertainty in constraints, specifically in complementarity constraints. There has been some other work in including uncertainty in the dynamics. And the way that that might work with our work is that you can include additional terms in your overall cost function to account for the uncertainty in the dynamic. So our approach broadly falls under the category of risk-sensitive work, and there has been some related work showing that the dynamical uncertainty can be included as additional quadratic terms that make you more sensitive to errors in the model as well.
Sounds good. And a follow-up to that is, so you are formulating the stochastic complementarity constraints. How does that affect your computation time?
Right, so if the uncertainty is very small, then the stochastic complementarity constraints are effectively just a smoothed out version of the original ones, and so the computation time isn't changed a whole lot. But if the uncertainty is a bit larger, which is the case where we actually get some of the robustness, then it does require an extra step in the optimization. So here we didn't do a direct comparison starting from the same point. We first generated trajectories without the cost due to uncertainty, and then we added the uncertainty cost and reran the optimization. And it would increase the time by maybe like a couple of seconds.
Thank you, Luke.
Hi, everybody, and thank you for tuning into our presentation on temporally interpolated funnel synthesis for nonlinear systems. My name is Taylor Reynolds, and I'm presenting this work on behalf of my co-authors, Danilo Meliuta, Aran Mizbahi, and Bechet Achikmeche. This paper provides an overview of our ongoing work on funnel generation for nonlinear systems. Our approach has been to leverage tools from the robust control literature, in particular quadratic Lyapunov functions, in order to design controlled invariant sets, or funnels. The funnels are designed so that their entire volume resides in the feasible space defined by a set of state and control constraints. By assuming the availability of a reference trajectory that is feasible for a general nonlinear dynamical system, we can capture the behavior of the nonlinear system using the linear differential inclusion shown here. This amounts to linearizing the system along a reference trajectory and then assuming that the remaining nonlinear terms satisfy a local Lipschitz condition. Using the quadratic Lyapunov function v, where Q is in general a time-varying positive definite matrix, we assume that a feedback law has the linear time-varying form shown here, and we seek a pair Q and K so that the Lyapunov function decays sufficiently fast along trajectories of the system for all possible nonlinearities. This is referred to as quadratic stability. Working in continuous time, we can carry out some standard analysis to obtain a differential linear matrix inequality that must be solved in order to satisfy the quadratic stability requirement that was just introduced. Note that we assume that Q bar and R have been pre-computed, a process that is fairly straightforward and based on the geometry of the problem's constraints. To actually solve this DLMI, we parameterize each time-varying component using coefficients from a unit simplex. This is equivalent to assuming that each parameter in the list can be well approximated by a convex hull of constant matrices. Plugging this parameterization into the original DLMI and working out the algebra leads to a set of matrix inequalities that, for certain parameterizations, are LMIs. Note that the Q dot terms depend on the chosen parameterization and are linear for first and second order parameterizations. As a result, Theorem 2 can be used to design final synthesis algorithms using semi-definite programming. To demonstrate this approach, we considered a simple planar quadrotor model whose equations of motion and constraint set are shown here. In addition to simple box constraints, there is a single ellipsoidal obstacle placed in the flight path. The funnel computed using a second order parameterization is shown in gray in the figure. It was obtained by using the procedure shown on the lower left. A set of test cases are shown in red, a subset of which start on the surface of the funnel entry ellipsoid in order to test the invariance of the funnel. Our code is available at the link provided at the bottom of the slide. Thank you, and we look forward to questions.
All right, great. Jay, are you there? Or Cherry, one of the authors?
Yeah. Hey guys, I'm here.
Oh, hey. Okay, so this approach was used for a vehicle. Can you comment on how this approach would work for other robotic domains, such as manipulators that may be operating in cluttered environments and come into contact with the environment?
Yeah, so we've tested this kind of baseline algorithm on, I would say, probably 6 or 7 different vehicles at this point, all in simulation. And so far we've seen that it kind of generalizes quite well to some of the other ones. So, I mean, for example, we've tested this on power descent, like rocket landing examples. We've tested this on, I guess, higher order quadrotor models, if you will, and some other kind of more simpler test cases. And so far, we've seen 2 things. We've seen one, that we can handle some fairly nasty nonlinear terms, like even some that don't necessarily have a closed form expression. And 2, that we can kind of handle a broad set of constraints. So, so far, everything that we've seen has been fairly promising.
Great, thank you.
I think there is a question.
I don't know if we have. I don't know if we have time for another question. So Taylor, I'm wondering. It seems like it has to work. You have this iterative procedure set up where you're sort of going between estimating this gamma parameter and contracting the Q bar. I'm kind of curious, what is the bottleneck in that iterative procedure, and if you could comment on how long it takes to converge.
Sure. Yeah. So the reason why it has to be iterative in nature is that actually the gamma parameter, like the local Lipschitz constant, kind of depends on the controller K that you get out. Once you plug that in and kind of close the loop, you can change the dynamics of the vehicle, obviously. So in that sense, it has to be iterative. And then the reason why we contract it is just to actually guarantee that that algorithm will converge. It's a fairly simple argument once we kind of set up the structure like that. And I mean, what we've seen, empirically, less than 10 iterations is usually pretty good, and you're solving a semi-definite program at each time. So for me, actually, the bottleneck is typically how do you estimate that gamma parameter? And there's that's kind of where I would see kind of the more there's more like wiggle room to design new and interesting stuff. But certainly, I would say both computationally and research-wise, that's definitely where the bottleneck is.
Great. I'm Shuri from Carnegie Mellon's Air Lab. I'm here on behalf of my co-authors to talk about our work on Adaptive Tube Library for safe online planning. Due to high-dimensional vehicle dynamics, unknown disturbances, and imperfect controllers, vehicles can experience tracking error, which is the deviation of the robot's actual position from the planned path. Despite a planned collision-free path, tracking error can still cause a vehicle to crash, as seen here. To handle these tracking error, we often plan with extra safety margins, which we can think of as an obstacle inflation or tubes around planned trajectories. However, presetting these margins is a delicate juggling act balancing safety and performance. This becomes especially difficult for dynamic environments with varying disturbances. Our key insight is to adapt margins on the fly based on the current measured disturbance uncertainty. To enable real-time adaptation, we pre-compute margins for multiple disturbance ranges, then choose margins online based on current measurements. First, we pre-compute tubes offline for trajectory library. For each trajectory plan in the library and each disturbance variance, we run many Monte Carlo simulations to find the vehicle's possible trajectories under the selected disturbance. From this, we fit a tube. Then we choose margins online given current disturbance measurements. At low uncertainty, the smaller tubes are used for collision checking, whilst the larger tubes are chosen when disturbance uncertainty is high. Here we show how this affects online planning. Given the same set of sensed obstacles, all three trajectories are available when uncertainty is low, at the left. Whilst at the right, only one is safe at high uncertainty. We validated our method on a vehicle with unknown model mismatch and showed we can safely capture its unknown tracking error. We showed the adaptivity of our approach under different disturbance ranges. As expected, we see higher performance when uncertainty is low. Finally, we compared our method to baseline static margin methods and showed it better balances safety and performance. In conclusion, we presented the adaptive tube library to adapt safety margins on the fly. Our next steps include running ablation analysis to find failure cases and linking our Monte Carlo-based framework to reachability analysis. Thank you.
Okay, great, thank you. Are the authors here?
Yep.
Wonderful. So one question, it's really interesting how you change the tube size based on the measurement of disturbance. Do you ever find that if the disturbance suddenly gets very high, all tubes will intersect with obstacles? And do you have any way of dealing with that?
Yeah, I think that's a great question. So I think that's actually what we're trying to do with like the simulated ablation analysis afterwards, is to kind of critically test these challenging cases. While we have not done so, I think what our method enables is you can kind of do this for multiple sets of trajectory libraries at different speed. So if we do suddenly experience a suddenly larger disturbance, then hopefully we can then transition into those lower speed trajectories that has a smaller safety margin.
That sounds really cool. Thank you so much. We have another question. Can you clarify what parts are offline and what parts are online? Are the trajectories pre-specified?
Yeah, thanks for the clarification question. So in the offline stage, we pre-specify like a set of trajectories, which we have as the trajectory library. And also offline for each of the disturbance variants that we're interested in, and also for each of these trajectory in that library set, we offline pre-compute essentially a reachable set using a Monte Carlo method. And then in online, we query which trajectories to use based on specific safety margins, based on the online estimated disturbance.
Okay, great, thank you.
I'm Catherine Shi, here with Cherie Ho, both from Carnegie Mellon University. We'll be talking about our work testing control barrier functions in an outdoor environment. A number of formulations exist that prove the safety of a system as long as certain assumptions are met. However, when applying formal safety tools in the real world, the system can lose safety should these assumptions made during derivation fail to hold. In this clip, we see that a state estimation error caused by a change in environment causes the quad rotor to rapidly accelerate towards the user, requiring manual takeover. In this work, we aim to identify key bottlenecks in bringing safety guarantees to the real world. Our test system is a quad rotor that uses visual inertial odometry for state estimation. For each test run, the quad rotor took off and flew autonomously to a goal, avoiding a single static simulated obstacle in its path. The start and goal positions varied for each run. We used a simple nominal controller as input to the safe control and an exponential control barrier function formulation to ensure safety. ECBS allow the designer to define a safe set and calculate controls on the fly that ensure the system remains within that set. The safe controller solves for the closest control to the nominal input that satisfies the safety conditions. Here we have an example trial where the drone avoids a single obstacle centered in the video. The drone is given a straight path to the goal. Note that safe control does not intervene until the system is in danger of striking the obstacle.
Using the setup, we completed 16 trials, 4 of which violated safety. We identified 3 key bottlenecks. The first bottleneck is state estimation error, where the dynamic scene change from the flying cone caused a sudden state estimation jump into the obstacle. This resulted in a high acceleration away from the obstacle, necessitating manual takeover. A possible solution can be incorporating state estimation uncertainties in a stochastic framework. This proposed approach can then be tested in challenging photorealistic environments for robustness testing. A second bottleneck is external disturbance, where here our system can experience gusts of high wind. A possible solution can be to use adaptive CVF framework to keep safe even in the presence of parametric model uncertainty. A third bottleneck is system delay, where we assume the system is affine to commanded acceleration, where in actuality there is a delay. A possible solution can be to use a discrete formulation that accounts for the input delay. In summary, we tested control barrier functions outdoors with a efficient-based platform. We identified 3 key bottlenecks and linked to works that separately addresses some of these. We are excited by a lot of these new work and advocate for a need for common benchmarking cases that replicates real-world scenarios to robustly test future safe control algorithms. Thank you.
Okay, great. Are the authors here?
Yes.
Hi. Great. So thank you so much for your talk. We have a couple questions. So first, maybe kind of potentially related, which bottleneck has the biggest impact on safety, and which bottleneck do you think will be the most challenging to overcome?
Yeah, so I think that is a really great question. So I think the 3 bottlenecks that we have, I think state estimation error is actually quite challenging because especially with the visual sensors that we have, it's unclear how we can predict these sort of errors. And I think the key challenge is what happens when there's a composite of all of these error, failure cases in general, and then how can we best handle these, like not just separately, but cohesively.
Okay, great. And a follow-up, how does this framework and the bottlenecks extend to things like irregular obstacle shapes or dynamic environments?
So one method of, for instance, dealing with dynamic environments is actually to define the safe set so that it, as in some previous sorts of ECBFs, that it's actually defined around the system itself rather than a static obstacle. As for irregular obstacle obstacle shapes. You can do it either using a combination of sort of an overlay of these sets, or you can attempt to find a shape that has the correct properties that will allow you to perform these calculations. But I don't know off the top of my head exactly how to do that.
Okay, great, thank you.
I'm John, and I am a PhD student at the University of Colorado Boulder with the Assured, Reliable, and Interactive Autonomous Systems Group. I'd like to tell you about our work towards an end-to-end framework for data-driven verification of unknown dynamical systems. Performance guarantees are important for deploying safety-critical systems. These guarantees can be generated through formal verification methods on two types of performance requirements: safety and liveness. Safety is exactly that. The system should not harm itself or its surroundings. Also, the system has to do something eventually. This is liveness. Traditional methods for verifying against formal specifications rely on having high-fidelity system models to perform model checking techniques. However, the verification results are only applicable to the considered model. If we have a system with an unknown component, such as a black box autopilot or a simplified model, then verification results do not hold for the underlying system. We want a way to connect this model to the underlying system to extend the result. Data-driven methods are gaining traction in overcoming these challenges. Take, for example, this autonomous underwater vehicle in a 2D space. While we do not have a full dynamics model, we can collect measurements to regress a model and bound the regression error. In this example, we are interested in finding initial states and resulting trajectories that satisfy and violate the property "do not enter A until B is entered." Our proposed framework can generate guarantees using a set of noisy state action measurement data from a system. To account for the modeling uncertainty, we generate probabilistic guarantees with respect to these system properties. By taking this uncertainty into account, the verification results on the regression model are valid for the underlying system. The framework consists of three primary components: a Gaussian process regression model of the dynamics, an interval Markov decision process abstraction, and a solver for the IMDP. We get tight probabilistic error bounds from GPU regression using RKHS-based analysis, and use these errors to define the transition bounds of the IMDP. The best and worst case system behavior depends only on the one-step transition probabilities that are computed by modeling it as a two-player game. In this game, one player chooses actions and the other chooses a feasible transition probability distribution. The verification result generally consists of three sets: a set that is guaranteed to satisfy the property, a set that is guaranteed to violate the property, and a set where no guarantees can be made due to high uncertainty. We can generate results for linear, nonlinear, and multimodal switched systems. This framework is our first attempt to connect machine learning regression to the verification of dynamical systems and safety-critical scenarios. We have a lot of exciting ideas for next steps, including online verification, controller synthesis for learned systems, and exploring other regression methods. Thank you for listening.
Thank you, John, for the wonderful talk. I have a couple of quick questions. Are you there?
Yeah, can you see me? Hear me?
Yeah. Hi, John.
Okay.
One question I have is around discretization of the state space. So it seems like you are computing these verification sets using a discretized state space. How does that affect your verification results? And do you have any thoughts on how we can extend these to continuous state spaces?
Yeah, so actually, we are beginning with the assumption that the state space is continuous, and the only requirement we have on the discretization is that if you have a state space that has labels like A and B, we just require that the discretization of the state space is consistent with however the continuous state space is labeled.
Got it. And then Tom has another question. What additional assumption do you need to make when you use ML methods? So for example, is there a goodness of fit assumption in the work that you've been doing?
Right, so that's something we're still trying to resolve ourselves. Using this RKHS-based analysis, we have to assume right now when we're using this Gaussian process regression that we choose a good kernel that can represent our function. And we've been working with kernels that can universally approximate any continuous function. And right now we're assuming we choose
like the hyperparameters well enough to approximate our function.
Got it. Thank you, John.
Yeah. Yeah, if there are no more questions, I'm happy to talk more offline.
Yeah, I think people will probably post their questions on the chat. So if you can stay for a little bit longer and answer any question on the chat, that would be great.
Yeah, I'm happy to. Thanks.
Hello. Today, Aziz and I will present our work on robust locomotion navigation in partially observable environments with safety guarantees. We propose a hierarchical task and motion planning framework that incorporates safety guarantees at each level. At each walking step, a temporal logic-based planner evaluates the robot and environment state and determines a safe action set to achieve the planner's navigation goals. A mid-level keyframe decision maker takes the action set and the current robot keyframe state and determines the next keyframe state based on reachability analysis. Finally, a low-level motion planner generates a center of mass trajectory using a reduced order prismatic inverted pendulum model. To guarantee safety at the task planning level, we construct a game between the robot and the environment using linear temporal logic synthesis. We generate LTL specifications that govern how the game is allowed to evolve. Within these specifications, we encode goal completion and collision avoidance properties. In the navigation game, we employ a belief abstraction to track the planner's belief of possible dynamic obstacle locations when the obstacle is out of sight. The planner is able to use this belief to guarantee which non-visible regions are obstacle-free. Here we can see two 2D simulations in a partially observable environment with the robot shown in blue and its belief shown in gray. Both simulations start with the same ground truth, but only the robot with belief tracking is able to guarantee collision avoidance and walk around the corner. I'll let Aziz take it from here.
In this video, we show that we are able to generate center of mass trajectories from the high-level actions using the mid-level keyframe decision maker and low-level motion planner. The Cassie bipedal robot is able to traverse through a cluttered environment. Here, we show the center of mass and swing foot trajectories of Cassie, as well as a 3-step turning strategy to avoid collision with the obstacle. As part of ongoing work, we would like to integrate reachability analysis into our framework to ensure that the mid-level selects a robust transition. In this figure, we compute the phase space reachability region of one walking step. First, we use the tangent and cotangent locomotion manifold to compute the final and initial robustness margin. Then, we compute the winning set. We specifically look at the intersection of the winning set and the initial robustness margin, which we denote as initial winning set. For any state within this set, a transition to the next keyframe state is viable. Therefore, dynamic balance safety is achieved. We use the size of the initial winning set as an indicator of the robustness of the transition. In future work, we would like to sequentially compose feasible discrete keyframe states via reachability analysis. We would like to acknowledge our lab mates and collaborators, as well as our funding agency. Thank you for watching.
Okay, great, thank you. So we have a question. If you find that the dynamic obstacles behave differently than you expect, so for example, they're faster than you initially assumed, can you update your beliefs on the fly based on these new assumptions?
So currently we cannot do that, or we currently have the assumption that we know what the limit of how far the dynamic obstacle is allowed to move a priori per step. But yeah, that's something definitely worth investigating in the future.
Okay, great. And we have a question. Do you know how well your current Cassie method will translate to the hardware? Some of the motions look quite dynamic and challenging to model.
So we have not tested it on the hardware yet, but that is a future step we need to look into.
Okay, great. Thank you so much.
Hi, my name is GS. In this presentation, I'll briefly talk about a joint work with Norman and my advisor. recent learning-based methods and optimal controls to complex sequential decision-making problems have shown promising results. However, questions persist with respect to their safety and robustness under uncertainty. Then, how do we know if the agents act in a robust manner? A robust agent should act desirably in different scenarios, including low probability events, and this is especially important to the problems where rare events are critical. Often, the evaluation relies on real-world testing and/or simulations with exhaustive search over entire state space, which are often too expensive. In this work, we propose a systematic approach to this evaluation problem for a two-player differential game. The idea is to find meaningful test cases by first answering which test cases should not be considered. These are the cases that are too easy or too challenging. Accordingly, the test cases of the interest are challenging, yet where a solution is guaranteed to exist for the agent. The problem we address is a model-based two-player game between an agent and a disturbance player. We define a performance metric, geobags, and a sub-level set of geobags as a collision set C, which represents the states where geobags is violated. For the disturbance modeling, rather than using the entire action space capital W, we leverage data to find realistic disturbance action. As opposed to a deterministic or probabilistic function, we model it as a set-valued mapping omega and learn it using a single-class classifier SPDD. Then we solve the optimization problem with respect to the disturbance player to compute the backward reachable set. The solution is disturbance winning set B, where the metric is violated under all possible policies. This means that the conditions sampled from B are too challenging. For the systematic evaluation, we sample the conditions from the complement of B and run the agent policy from the initial state and check if the metric is violated over the time horizon. We demonstrate our framework in a simple autonomous driving example for a car following scenario where an adaptive cruise control policy is evaluated against a leading vehicle. The disturbance set valued mapping is learned using naturalistic driving dataset SBMD. We obtain the backward reachable set and its complement and we evaluated the policy using them. The figures indicate that there exist test cases where a solution is guaranteed to exist. However, the policy failed the test. Finally, we described an example test case where the agent failed. However, a solution is guaranteed to exist. This is the end of my presentation. Thank you for listening.
All right, thank you for the great talk. Is the speaker here?
Yep, this is GS speaking.
All right, GS, perfect. Just a couple of questions for you. So first, can you comment on the computational complexity of each kind of major component in this approach and any bottlenecks or resulting limits you might have?
Yeah, so first obtaining the data-driven disturbance set, it's done in offline, so there's no bottleneck, but the real bottleneck comes in solving Hamilton-Jacobi-Bellman equation. Right now, our application, the experiment, is monotonic system with respect to Hamiltonian, so we don't really check across all the inputs and disturbance actions. We have extremal inputs and disturbances, then we only need to check for those extremal cases. So, but for a non-monolithic system, there's definitely curse of dimensionality and we have to address. Right now we're working on that for as a future step.
Cool, thanks. And just one last question.
Sure.
How sort of realistic is it to just sort of brute force, sort of evaluate a policy directly with the sort of random disturbances from whatever distribution or something like that? Is that at all tractable? Or is it tractable in only some cases or just totally intractable?
If is your question about tractability, about having the disturbances is random disturbances that can emit For
Yeah,
example,
I think that's basically my question. Yeah. Yeah. Right.
yeah. So if you have a bigger like upper limit and lower limit, bigger W's, then you have bigger disturbance winning set.
Mm-hmm.
But then evaluations against those uninteresting cases where you have an easy solution would end up being uninteresting and waste of time. And that's one of the motivations that why we use data-driven disturbance set, where we only test against the observed disturbances at a given step, at a given state.
Cool. Thanks so much.
Thank you.
Hey everyone, my name is Kyle Ray, and today I'm going to talk to you about multi-objective POMDPs for robust autonomy. In the real world, we don't just want to maximize a main objective, such as this autonomous vehicle navigating a T-intersection. We also want to maximize a measure of safe control. And for the case of autonomous vehicles, we also care about maximizing legal constraints and a measure of social acceptability and so on. And so in order to properly model this, we really need a multi-objective model that lets us capture the robust autonomy concerns within it. We propose the topological POMDP, which extends the normal POMDP by including a vector of rewards. And this vector of rewards, we relate them through a DAG. Attached to each of the edges of this DAG, we assign slack constraints. And the slack really represents how much you're willing to sacrifice in one objective in order to improve the value of another. A simple case is a chain, where we call it a lexicographic POMDP. Another case is a constrained POMDP, where it's a fan structure. And so a topological POMDP is any such relationship. In a T-POMDP, we also maximize expected return using a value function. However, we're also subject, for any node I, we're subject to the constraints that all the ancestors satisfy their slack. There's an approximate algorithm for this called local action restriction, where we have the full action set available at all the beliefs, and we step down the DAG, pruning the actions that are outside of slack, until finally we're left with a set of actions at the end. When we concern ourselves with the autonomous vehicle scenario, what we would hope to see is that when you have zero slack for, say, an aggression objective, you get relatively aggressive behavior. When you set zero slack to some smoothness objective, you may get more smooth behavior, but it's a bit slower. And so when you allow a little bit of slack for both objectives, then we can get some interesting behavior, such as this, where the autonomous vehicle slowly stops at the stop line, edges forward for visibility, and then proceeds onward when it's confident. In conclusion, T-POMDPs are multi-objective reasoning models, and they let us model the robustness concerns within their objectives. We describe their relationships using a preference graph and associate slack on the edges, and it allows us to tune the robot behavior to get different results. Thank you for your time.
Okay, great. So I believe Kyle is here on the call.
Yep, can you hear me?
Yes, great. Thanks, Kyle, for the great talk. So I was wondering if you could maybe say a bit more about how you go about tuning the slack, and in particular, how this framework can be used to reconcile, potentially conflicting objectives, like in your example with aggressiveness versus smoothness. I can imagine that, if you have relatively tight slacks, it might be that the optimal solution for aggressiveness is pretty bad for smoothness, and the optimal solution for smoothness is not very good for aggressiveness. And so it might be that when you get to the common descendant node, you just find that you have an infeasible problem because you can't be near optimal enough for both. So I'm just curious, what's a good way to adjust the slacks to sort of do this trade-off?
Yeah, that's a great question. So there's kind of two in there. So one is, how do you choose the slacks? One of the benefits of this approach, as opposed to like scalarization, where you take a lot of objectives and you kind of weighted sum them or something, is that it preserves semantic meaning with the objectives. So slack has the same units as the objective you're maximizing. If it's minimizing time, you're sacrificing in units of time for another objective. So it's easier to pick the slack amounts. In terms of infeasibility, so just like a constrained MDP or constrained MDP, you can get infeasibility if there's no solution within the budgets available, right? So you can also get that, of course, with a topological POMDP. When you have a chain structure, you're only limiting in the policy space. You're limiting the space of policies available every time you do one of the steps. When you have the constrained, anytime you have multiple incoming edges, you're taking an intersection, so you can get infeasibility. But yep, I guess that's all the time I have. But we can talk offline if you have more questions.
Sounds great. Thanks a lot, Kyle.
My name is Chizan, a Nissan researcher at the Alliance Innovation Lab in Silicon Valley, and I'd like to take a few minutes to introduce the topic proactive risk mitigation and reactive control for safe and smooth automated driving. In addition to predictable static and dynamic objects, autonomous vehicle must also handle unpredictable hazards such as parked car doors opening, cyclists falling, or pedestrians stepping off curbs. In this video, we have a scene where the right lane is taken up by a bike race. The cyclists stay in their lanes the vast majority of the time, but accidents happen on rare occasions and the drivers were still able to avoid them successfully. It's clear that human drivers mitigate such risk through a combination of proactive and reactive lateral and speed maneuvers, and this work is about encoding such behaviors in AVs. To do so, we have created a pipeline that has both sides to it. The key ideas for designing the proactive mitigation component is that false positives are resolved as the AV approaches, dynamic hazards have incursion speeds, and reactive capabilities of the AV are known. The proactive planner is a constrained optimization to compute a smooth long horizon trajectory in anticipation of static and dynamic objects and detect the hazards. The optimization has a cost function that penalizes state tracking errors and control effort, subject to equality constraints that enforce the process model and inequality constraints that enforce state and control limits. The control limits of the planner are rather strict relative to the reactive controller and provide a smooth trajectory. As for the state constraints, we consider the reactive capabilities of the car by using kinematic approximations, where we estimate the maximum lateral displacement that the reactive controller can execute before reaching the hazard. This approximation is used in conjunction with models of hazards to produce proactive maneuvers that retain the reactive capability to respond to emergencies. While evaluating constraints, the proactive planner produces a minimum risk maneuver zone, a region surrounding the planned trajectory with a low risk of collisions at time of arrival for emergency maneuvers. If the gap is too small, we proactively slow down. If the gap is big enough, we can proactively avoid the hazard zone altogether. The reactive control module, in contrast to the planner, uses a high-fidelity vehicle dynamics model, high-frequency computation, and aggressive motion limits to avoid obstacles that may appear too fast for the planner to respond to. Here's a short clip of our experiment. The first proactive maneuver is to move to the right since there's enough space. For narrow gaps, we slow down proactively and keep to the side. And since we're already planning to move to the left, the vehicle passes by the opening car door smoothly. And since we're already slowing down, we also come to a stop smoothly.
Great. So I believe Chizan is with us on the call. Chizan, can you hear me?
Yep, I can. Can you hear me?
Yes, great, loud and clear. So this is a really cool approach, and you know, it looks very exciting, and like it definitely shows some promise. I'm wondering if you have thought about how we could go about combining multiple sources of risk that might couple with each other. So for example, if you're approaching a parked car in a narrow road, but you're also being followed by a tailgater, which might make, for example, abrupt braking risky in itself.
Yes. So we have done combinations of different hazards and risks, but that specific scenario that you mentioned will definitely make a really interesting future work. That's an interesting consideration. We have to consider the people behind us as well. So yeah, I'll list that down as future work. I don't see why it's not possible in this framework. It's a pretty general framework, I think. And we're still working on diversifying the scenarios and types of hazards. So yeah, that's a great possible scenario that we can look at in the future.
Sounds great. And we seem to have a question in the chat from Jason Choi. Can this method adapt to various lane shapes, like for example, a curved lane instead of straight?
So yes, it can, but I think the current approximation, kinematic approximation, assumes a straight lane, and that is only meant as a placeholder, a simple placeholder for more complex, more sophisticated approximations. And yes, I would put that under future work as well, but I don't see a reason why that's not possible within this framework.
Sounds great. Thanks a lot.
Hello. This video presents our paper about multi-adversarial safety analysis for autonomous vehicles. How multi-Jacobi reachability analysis can be used to find safe strategies around unknown components of a system. However, in some cases, reachability analysis can be too conservative, and it may be the case that guaranteeing safety is impossible. For example, in the simulation on the left, reachability is able to find a set of safe states that keep the autonomous vehicle from crashing into the other car. On the contrary, reachability fails to uncover any safe states for the simulation on the right. Note that the X's on the simulated plots represent the relative states between the autonomous vehicle and the surrounding vehicles. Therefore, in this work, we'll study how to reduce conservativeness in safety analysis to guarantee safety in more dense driving environments. Let's consider a three-car driving scenario whose dynamics is described by a double integrator of relative positions and velocities. We consider a differential gain between the system's control, U2, and the two adversaries, D1 and D2, also known as the system's uncertainty. The goal is to keep the subject vehicle within its constrained blue and green set, while the two adversaries actively try to get the vehicle to leave this set. We formulate two modeling strategies for D1 and D2 and study the differences between the sets that they produce. First, we consider a baseline strategy where D1 and D2 are assigned to be the acceleration behaviors of the first and second human drivers respectively. However, as shown below, there is no safe set for the autonomous vehicle because in the worst case, there's always a winning strategy for the two adversaries. However, if we consider subtle interaction behavior between the subject vehicle and its follower, we may be able to uncover hidden safe strategies for the autonomous vehicle. Therefore, we'll consider an alternative strategy where D1 stays the same, but D2 is assigned to be a psychophysiological component in the model that relates the behavior of the autonomous vehicle to the behavior of its follower. Here, instead of assigning D2 to the overall acceleration of the second human, we assign D2 to be its reaction time, a component of its actual acceleration behavior. As shown on the right, the alternative formulation is able to uncover hidden safe states for the controller. In conclusion, we may need to incorporate better information structures of human behavior for safe driving. However, by choosing a specific model structure, we run the risk of not being able to capture human behavior some of the time due to the limitations of our model. Therefore, as next steps, we'll examine other models and learning strategies to better understand these trade-offs. Thank you.
Okay, great. The authors here?
Yes, I'm here.
Hello, okay. So we have a couple of questions. First, in the model of the human driver that you added in, it seems your uncertainty is around reaction time. Have you thought at all about estimating this reaction time for the nearby drivers online to kind of reduce this uncertainty further?
Yes, that's actually what we want to look at as next steps. We want to see how we can do this in real time in order to provide more robust guarantees. So that's actually a next step. We want to test that.
Okay, great. And we have another question to ask if you could talk a little bit more about your thoughts on integrating learned control strategies for the vehicles into this reachability analysis.
Learned control strategies? Can you be a little bit more specific?
Yeah, the question says, for example, to learn a function for each other driver which maps from states to actions and then optimize over this during the reachability computation.
Okay. So I guess to clarify the question, are you asking how can we introduce controllers in sort of doing this like online sort of estimation, or is this or am I confusing the question?
Why don't I ask, Andrea, you were the person who asked this question, right? Could you clarify?
Yeah, my question was just if we can use, for example, data to extract how the other agents, like the other cars, might react. For example, like the degree to how adversarial they're going to act. If we can learn that offline, for example, then plug in this like level of adversarial behavior that they're doing, and then optimize over this like safe set. It's kind of like a pre-step before an online solution.
Right. Yeah. So I think that's definitely possible, and I think that would be that would definitely be an interesting thing to try out, because like you could, I guess, in the reachability framework, a component of that is specifying a strategy for the disturbance. And so if you have a controller, you can plug that in. I think what would be interesting in that is to study like whether that would lead to more conservative estimates of safe sets. So I think that would be an interesting next step to also look at, to like incorporate like a controller or policy for how adversarially the vehicle would act, and then plug that into the framework.
Thanks.
Yeah.
Great, thank you.
Hi, my name is Jinan Shi, and I'm here to present our group's work on Teaser++, fast and certifiable point cloud registration. In this work, we are interested in solving the problem of robust point cloud registration. Specifically, we want to have a solution for given feature correspondences, finding the best transformation that can align a model point cloud with the same point cloud. However, in practice, over 95% of the given feature correspondences can be incorrect. To solve this problem, we developed an algorithm called Teaser, which stands for Truncated Least Square Estimation and Semi-Definite Relaxation. Our Teaser algorithm decouples scale, rotation, and translation estimation, and uses a so-called truncated least square cost function to solve them. Essentially, what the truncated least square cost function does is it assigns the fixed cost to residuals greater than a threshold. Here is a diagram showing the pipeline of our algorithm. First, we estimate scale using adaptive folding. Then we estimate rotation using semi-definite relaxation. And finally, we estimate translation using component-wise adaptive folding. Unfortunately, in real time, solving large-scale SDP is very slow. Therefore, replace the middle part rotation estimation with an algorithm called graduated non-convexity. Essentially, what graduated non-convexity algorithm does is it solves the non-convex TRS estimation by starting from a convex surrogate cost function and gradually increase the non-convexity. One benefit of using such algorithm is that we can have a fast certification algorithm that basically give us an idea of how close our estimate is to the real global optimal. We run our algorithm on standard benchmarks. Here is showing the rotation error with respect to outlier rates. While RunSec and FGR fail teaser and teaser++ remain accurate. In addition, teaser++, the one that with GNC algorithm runs blazingly fast. It can finish solving the problem within around 20 milliseconds for problems with 1,000 points. Here is an application for teaser++. Basically, match RGBD scans given correspondences generated by 3D SmoothNet. So the green lines here show the inlier correspondences, and the red lines here show the outlier correspondences. Here is showing the final alignment with the teaser and the ground truth alignment. As you can see, the teaser alignment is very close to the ground truth alignment. Thank you for your attention, and our code is publicly available at GitHub.
Are the authors online?
Yes.
Hey, great. Yeah, thanks for the talk. I'm wondering if the optimization program can degenerate or result in multiple solutions, say if the point cloud is symmetric. For instance, if you have a spherical object, how can we really provide certifiable guarantees in such cases? Because you can have multiple solutions, right? Or can be degenerated.
Yeah, that's a great question. In cases where there are, like, for example, two symmetric solutions, then it is possible that we have a certificate that says it is close to the ground truth, say within 5%. However, it can be the complete opposite of the actual ground truth transformation.
I also want to add that so in the usual case, when you have two solutions that have the exact same cost, if you solve the SDP, it's going to give you two solutions. Actually, it will give you a rank 2 solution, basically a rank 2 matrix, and then from the rank 2 matrix, you can do some post processing and then get the two individual solutions that are actually the two solutions that you want. But in most cases, this is not going to happen because usually the cost will differ, by even a very small floating number. So it's unlikely going to happen.
Right. So we have a follow-up question from Prayas on the chat box. For robot vision applications, have you thought about what the robot should do in case of a certificate of estimation failure?
Yeah, I would suggest in that case, it would be wise to pause and perhaps get another, say, 3D scan or image.
Also, I can add another point that right now we're working on how can a robust backend help feature learning and feature detection. So usually in the case that when you have a failure in the estimation, that usually means that your front end is bad. And then in that case, you probably want to back propagate to the front end and then help your front end learn something better. So in those cases, we believe that the robust backend can actually feedback to the front end. So that's our goal.
Right. So we have one last question. If the 2-point clouds are different scales, how does it converge? I believe it's invariant to scale translation and rotation.
Yes, that's correct. We can solve for scale.
Okay, so it still converges, right?
Yeah.
Okay. Yeah, so if there are some other questions on the chat box, please answer to them. Okay, thanks.
Thank you.
My name is Francisco. I'm a research engineer at 5AI. We're a UK-based autonomous driving and tools company, and I'm going to present some work we did on a safe motion planner for urban driving. So the first thing to understand is that autonomous driving is a safety-critical domain, so we need to be able to give some guarantees on the motion planning methods we choose to deploy. From this view, we've realized this problem is a hierarchical one. Collision avoidance with users and borders must be satisfied, and so they're hard constraints, whereas progress and comfort are only desired, making them soft constraints. And if we want to encode this in a scalable way, constrained optimization stands out as a viable option. And typically it's nonlinear constrained optimization, which we're trying to optimize states and inputs over a finite horizon, such that they minimize a certain cost function, which includes progress and comfort terms, while satisfying nonlinear vehicle dynamics, as well as staying on the road and avoiding collision with other road users. This is a typical formulation, and it's usually solved as a nonlinear model predictive control, or NMPC, problem in a receding horizon fashion. But the issue here is that this process doesn't converge to a feasible solution in a lot of scenarios. And when it does, it converges somewhat slowly into a solution fairly close to the initialization given. So solving this in an NMPC fashion is a fairly biased process towards keep doing what you had already planned, even if there's a lower cost solution using a different initialization. So we propose to initialize this nonlinear problem with a linearized version of it. This linear solution might not be kinematically feasible, but we then use it to initialize the NLP problem, which is. To achieve this linearization using a mixed integer programming formulation, considering linear non-holonomic vehicle dynamics versus the bicycle model in the nonlinear problem, piecewise linear approximations of the borders as opposed to C2 functions in the NLP, and approximate other users with axis-aligned boxes instead of the continuous ellipses in the nonlinear case. And with this, we're able to solve some complex scenarios, such as this example of overtaking static vehicles with a dynamic vehicle on the oncoming lane, as well as others that we present in the paper. In terms of results, we compared different one-shot alternatives to our MILP initialization in a large data set of residential driving problems, and conclude that our initialization versus these other heuristics, such as all zeros or a constant velocity one, leads to superior convergence, but it's also better in terms of cost achieved and the runtime of the second stage, or the NLP stage. When compared to a nonlinear model predictive control baseline, in which the NLP is initialized by the previous solution shifted by 1, we see that our solution solves a higher percentage of examples, outperforming the NMPC baseline in progress and comfort metrics too. The current implemented solution is slower than the NMPC one, but it takes at most 1 second to produce an 8-second plan in about 87.5% of the examples in the experiments, which makes it feasible for slow-moving situations like residential driving. And that's pretty much it. Thank you for attending.
All right. Thank you, Francisco. Are you here?
Yeah, I'm here. Thanks.
Perfect. I got a couple questions prepared, and I'll ask anything off the chat. So let's get started. So basically, the first one I thought of was, all of this mixed integer initialization is wonderful, but can you comment on how much of the total computation budget is occupied by the initialization?
Yeah, so actually what we ended up doing is solving the MILP stage in receding horizon, because MILP problems are typically quite expensive. So the NLP stage in our empirical evaluation takes about 30% of the runtime versus 70%, which is kind of the MILP stage. But it does yield better solutions overall. So future direction of this work would be to improve the MILP stage runtime by using approximate solutions or specific range and bound algorithms.
Sure, thank you. And just one more can you give a bit more intuition about some of the way you formulate safety constraints in the MILP?
Sure. I think I might have missed a little bit of your question, but I think that I understood the gist of it, if I'm not mistaken. We formulate them as axis-aligned bounding boxes. So it's essentially we use the mixed integer formulations of these Boolean constraints as a way to introduce piecewise linear functions, which define these axis-aligned bounding boxes. This is just for a purely, they wouldn't need to be theoretically axis-aligned bounding boxes. They could be just other types of piecewise linear functions, but this is the simplest formulation that leads to faster runtimes.
Thank you very much.
Thanks.
All right, so thank you to everyone who just attended, to all of our contributive talks, our authors, and also all of the participants, you guys who have been listening. So we're gonna take a short break now. We're gonna return in a little bit under 15 minutes, and we're gonna proceed with 2 more of our invited talks. So see you guys soon.
Hello, everyone. Welcome back. I hope you had a nice opportunity to get up and stretch your legs or have a nice coffee. We're back right on time at 1:15, and we are now moving back to our invited talks. For our next one, we are lucky to have
Tim Barfoot. Tim is an
associate professor at the University of Toronto, where he runs the Autonomous-Based Robotics Lab. Tim actually got his undergraduate and doctoral education at the University of Toronto, but before returning to join the U of T faculty, he spent 4 years at MDA Space Missions, developing navigation technologies for autonomous vehicles, both in the ground, on the ground and in space. Tim has made a variety of contributions to robot navigation in unstructured environment, localization, all the way to motion planning. In addition to a long list of contributions to robot state estimation and visual navigation, he is responsible for a number of algorithmic improvements in motion planning, like informed RRT star and BitStar. And I believe he likes to refer to this as doing the cleanup of motion planning. Tim was also a visiting professor at the University of Oxford in 2013 and recently completed a leave as Director of Autonomous Systems at Apple between 2017 and 2019, although I suspect he's not going to be telling us what exactly this involved. In any case, we're very excited to have you, Tim, and take it away.
Great. Can you guys hear me and see my slides? Yes, you can. Okay, I see some nodding heads. I'm going to begin. So thank you very much to the organizers for the invitation to come and give this talk. I struggled a little bit to pick something that fits the theme of the workshop, so bear with me. This was the closest I would get in my nearest neighbor search. I'm just going to start my stopwatch there. Okay, so I just wanted to motivate the talk a little bit with a couple of videos of systems that we've built in the past. So this is a robot that's navigating visually. It's a system that we call visual teach and repeat. The idea is to sort of take a robot to a new environment such as this one, and from single demonstrations of these paths that you're seeing on the ground here, the robot should build a map and then be able to sort of robustly navigate on these paths, or this, in fact, network of paths forever, essentially, after that. What you're seeing is autonomous repeat of one of these paths right now. So the robot's got a single forward-looking stereo camera, a single laptop. It's not using any deep learning. And you can kind of see after a couple of weeks of living in the field and repeating these paths, we've actually etched them into the earth just because we've been driving them so many times. So these ruts that you're seeing the robot driving in are actually just from the robot repeating these paths so many times. So that's one example of a system that we've built in the past. So no GPS, just navigating visually. And by the way, even from these single demonstrations, we'd like the robot to be able to continue to repeat the paths despite the fact that the lighting and the weather have changed, or perhaps even that the vegetation has grown. And we've actually been able to build systems that can do that in the past. So you can look at some of our past work for that. Another example of a system we built, looking back even a little further, is this underground mining truck. So we built the autonomy system for this. This is actually laser-based. You can kind of see old school planar SICK laser rangefinders mounted forward and backward looking on this truck. And again, this was sort of a learning from demonstration problem. So the robot had to be driven manually to define the routes that it could drive on. And now it's autonomously repeating those routes, even at high speeds, actually, almost as fast as the human drivers can do so. And then a third motivating example, this is actually our self-driving car system. This was built mostly by undergraduates at the University of Toronto. This is Zeus. It's competing at M-City during something called the SAE Auto Drive competition last year. So this is sort of your standard fare for self-driving, lots of different pieces fitting together. And you can kind of see Zeus here just predicting what this small robot pedestrian is going to do so that it can stop safely. So these are the kinds of systems that we've built in the past. I'm not going to talk a lot about field robotics in this talk. I'm going to get into some other stuff. So if we just go back to that first example of the robot following paths using stereo vision, here's sort of like a straw man architecture diagram for what the autonomy system for that might look like. Sort of your standard stuff, extract some features from the stereo camera, use those to do state estimations such as estimating motion using visual odometry, matching against a map so the robot knows where it is, passing those state estimates over to some kind of path tracking control, referencing that against the shapes of the paths that we want to follow, and eventually sending some commands to the robot. And of course, that all sounds very standard, and we all know that to get a system like this working, there's a whole bunch of other tasks that we also need to take care of even before we can turn the robot on in its autonomous mode. We need to think about what features we're going to use. You guys can see my mouse if I wave it around. Yeah. We have to do some mapping, of course, in advance. We need to calibrate the sensors, not only the internal parameters, but where they're located on the vehicle. We need to do some kind of dynamic identification of the robot, some path planning. And you can kind of see that there's a lot of things that have to funnel together to finally get sent to the robot, even in this fairly simple problem that doesn't have a lot of dynamic objects. And so after building a few of these systems, I'd like to maybe share a couple of general observations that I'm sure many of the people attending this workshop have also thought about. So putting that up on the right. One thing that's bothered me after building a lot of different robot systems and putting them in the field is that really our architecture diagrams, although they're very nice and modular, often our algorithms, I'm using this catchphrase now, our algorithms meet for the first time in software. And this is something that's really started to bother me. We've kind of gotten to this place where we've compartmentalized the development of our robot systems into these sort of standard pieces that we work on, and then we try to get them to meet for the first time in software. And I think even we're starting to get better at propagating uncertainties and things like this, but we're a little bit loose on our interface control, I would say, between the different pieces. Another observation that others have talked about in this workshop is that there are often mismatches in the assumptions made by the different modules in the architecture. We could be using a different robot model for path planning and estimation, and this can lead to problems. And I guess my observation would be that we've kind of pinned our hopes to bookkeeping the uncertainties through this funneling of things to the commands that finally get sent to the robot. And that's good if we can start to make smart choices at the control level based on the uncertainties, but there are a lot of sources of uncertainties. And I guess my experience has been that it's been really hard to ensure that the uncertainties that finally get fed into the last step, the control, are actually meaningful. And it's because there have been so many places that they can creep into the problem. Another thing is, I don't think we really make any guarantees at the full system level. At least in field robotics, we're often resorting to sort of assembling these pieces and then just testing things in anecdotal trials. And I'm as guilty of that as anybody else. And finally, I think it's just really hard. I don't know the answer to this, but it's really hard to write down any kind of verifiable requirements at the system level, given the variety of complex situations the robot can interface or face in the world. I don't have the answers for all of these questions. My talk, if you're hoping, is going to answer all these questions. It's not. I'm going to start to maybe talk about the first bullet here, which is our algorithms meeting for the first time in software. So I'm going to tell you a little bit about a framework that we've been working on based on variational inference that tries to start from a single loss function, so hence the cheeky title of the talk. We think about the graphical model of our system as sort of the first-class citizen, and then we've been thinking about using this variational approach to doing both state estimation and learning all the parameters of our system. And well, we'll get into the details. I'll give you a couple of examples of that working in practice so far, and then I'll give you a future outlook. And I'd like to introduce something that we're calling in our lab the Mr. Potato Head Challenge, which starts to get into sort of this idea of building general autonomy templates that we could fill in with data. So watch for that at the end. Okay, so into a bit more of the technical details, we like to think of the graphical model of our system as the first-class citizen. So many of us use graphical models that look like this. We have X representing the robot trajectory. We have some inputs U and some sensor outputs or desired outputs Y. And you can kind of see we can break this into the past and the future. And this is sort of a nice way of linking everything together mathematically, right? There's basically one graphical model. And perhaps what we might want to do in building a real system is to sort of learn the motion and observation models of our robots, which we could parameterize that with some parameter theta. And then if we could figure out what those thetas are, which we often do through sort of ad hoc tools, we can start to hold some of our variables fixed and try to infer the others. So I've sort of highlighted green things that we might know. We might know the past inputs and outputs. We might know some desired future outputs, and we might want to try to infer what the control inputs would have to be to produce those desired future outputs. So depending on which variables you hold fixed and which ones you try to infer, you can pose lots of different inference problems on this graph. And so I've been looking at how to connect different tools that we have at our disposal now in robotics within a single mathematical framework using graphical models. And I sort of happened across this collection of papers, and in one particular paper by Zubin and Sam, actually over 20 years ago now, where they were looking at how to combine classic state estimation tools with neural networks. This, of course, was way before deep learning, and the tools were a bit different, but I took a lot of inspiration from this paper. And so what we've been looking at is sort of the fundamental building up of the input-output model of the robot from data. And so there's lots of things that this depends on, these parameters theta, that could be things like sensor calibrations, measurement covariances, network weights representing deep neural representations of nonlinearities in our system. And so the idea of trying to come up with all of the values for these parameters, the system identification problem that has to happen before we can even do any autonomous operations, can then be posed as this nice learning problem where we can essentially try to start from a training data set and try to maximize the likelihood of the data given the parameters. And Zubin and Sam in their paper showed that they could do this very elegantly using this expectation maximization framework. And then once you've done that in online operations, you can hold the parameters fixed and try to do something like infer the future inputs that you would need to produce some desired outputs. And so this is what this is the path that we've been following with this work. We can use the usual variational decomposition to take the negative log of the likelihood of the data given the model. And that can break into these standard two pieces, one that's always going to be less than 0, and the so-called evidence lower bound, actually for us, the negative evidence lower bound, or this V that I've defined over on the right in the green box. And so this is the one loss that I refer to in the title of the paper. And the idea is that from a training data set, we can try to minimize this V in order to learn our system, and then also minimize it to do latent state estimation or inference for some unknown variables. So in the training phase, in the EN framework, in expectation, we hold the theta fixed and optimize for the distribution over the latent variables. In this case, this could be the robot's trajectory. And then in the M step, or in our case, a minimization, we hold the distribution over the latent state fixed and try to optimize for our parameters. And this is very general, right? We can apply this to almost anything. And then the nice thing is we can choose different tools to represent different parts of our robot learning system. For example, we might want to choose a deep neural network to represent the motion model or the observation model of the robot, and we can, in this M step, learn the parameters or weights of that neural network. And of course, Q of X has to be, the distribution of our latent state has to be chosen from some appropriate approximation family. In our work, we still use Gaussian, but one could imagine doing something more sophisticated than that in the future. Right, and so going back to our problem, the E and the M step, essentially, in the E step, we're holding all of the models fixed, the motion and observation models, and we're trying to do state estimation. So this is just classic state estimation. And in the M step, we're holding the distribution over the latent trajectory X fixed, and we're trying to learn or improve some of the model parameters in our system. And so we kind of like this framework because it lets us put together lots of different pieces to do state estimation, calibration, possibly even control, because people have posed control as inference problems, all within one neat and tidy framework. So that sounds great. I'll skip that point. It turns out as we started to do this, to try to do this in practice, we found that actually variational inference, while very common in machine learning and computer vision, it's actually a little less common in robotics. And we found that there actually wasn't a good tool for even trying to do variational inference for Gaussians for the size of problems that we tend to deal with in robotics, right? So we could imagine having a very large trajectory that we want to do inference over. And it turns out there aren't really any great inference tools. What we tend to do in all of our practical tools is we use maximum a posteriori estimation. So we tend to just look for the most likely state. And so right back at the beginning, we found we actually had to develop a new inference engine that would let us do estimation over large scale problems in a variational sense. And so we put out this paper earlier this year, exactly sparse Gaussian variational inference with application to derivative-free batch nonlinear state estimation. And I won't go through all of the details of the paper, but essentially what it lets us do is come up with the best Gaussian in the sense of KL divergence from the true posterior, where we're now optimizing both the mean and the covariance of the system, not just the mean, which is what we typically do in a lot of our robotics inference problems. We showed that this is actually tractable for real world problems with large state size and even loops in the graphical model. So we can apply it to SLAM and bundle adjustment and these kinds of things. As a byproduct, it turns out that we are able to actually do this even without taking derivatives by introducing sigma points or other forms of Gaussian quadrature into the problem, which is actually kind of a nice thing. I think it's the first batch variational inference engine that we can use in robotics. And then the nice thing is because we built this on variational inference, it lets us neatly fold in parameter estimation into the works so that we can actually take this expectation maximization framework and learn parameters of our system. So it's a very general paper. I encourage you to check that out on arXiv if you're interested. In a little more detail, I'm looking at my clock, I'm at 14 minutes. We have this loss function, which is this negative evidence lower bound, which we can rewrite as I have here on the slide. X is our latent state. This is the algorithm we come up with. It's actually a form of natural gradient descent. So it's an iterative solver that looks a lot like maximum a posteriori, except we have these additional expectations over here on the right-hand side of our system. So this is the inverse covariance, and we're taking sort of, you think of it as Newton's method, but you've got an expectation sitting here on the right-hand side. The problem is this expectation is over the latent state, or the distribution actually. So that's a bit of a problem because we don't actually want to ever reconstruct the full covariance matrix in a lot of our problems because that would be expensive. However, because a lot of our problems in robotics actually factor, we can actually say that our posterior factors, and so we can write the negative log of it as a sum of terms. And when we exploit that and sort of plug that in, the expectations that we have over on the left reduce to just expectations at the factor level. So for those that are interested, they can dig into the paper, but the implication of this is that we can do this big batch variational inference problem where we never actually have to construct the full covariance matrix to do these expectations on the right-hand side. We actually only need the non-zero blocks of the covariance that correspond to the inverse covariance. Sorry, we only need the blocks of the covariance that correspond to the non-zero blocks of the inverse covariance, which makes it fairly efficient. And there's this obscure paper from 1973 that allowed us to figure out how to do this very efficiently, even when our graphical model was very loopy. So in practice, here's just an example of this inference engine working on a SLAM problem. So it's a loopy graph. Because we've got these landmarks that we're also estimating, not just the robot trajectory, very toy problem. But on the right, you can kind of see that, and actually we made this highly nonlinear by forcing the robot only to have a range sensor. Actually, no, sorry, just a bearing sensor and no range sensor. So kind of like a monocular problem. And we were able to show that we can actually get more accurate and more consistent estimates using this solver, which means that our uncertainties are hopefully more useful than if we'd done this just using maximum a posteriori and the so-called Laplace approximation for the covariances, which is what we mostly do. So I want to give you 3 examples of learning some parameters now. So that was just estimations. Here's some examples of learning parameters. So back to the toy problem where we know our map of where all the landmarks are now. So it's just localization. And we're going to learn the motion model and the covariances of our system. Sorry, we know the motion model and covariance, and we're going to learn the range bearing model, including the location of a small LiDAR that's on the robot. So we're doing sort of calibration and system identification together. The next example is a robot driving around localizing against a big LiDAR map. In this case, we tried to learn noise models. So we know the motion and observation model functional forms, but we don't know the noise properties of these sensors. In fact, we learn, it's a bit too detailed to get into, but we learned some hyperparameters associated with the distributions of the noise models, both for the motion and observation models. And the third example, which I may actually just jump to that one given the time, is we're doing lidar odometry. We know the motion model, and we know that we're going to be observing 3D landmarks, and we tried to actually train a deep neural network within this framework to figure out what to pay attention to in the lidar scan, and actually to also learn the associated covariances that would come along with observing particular types of 3D landmarks. And in all of these examples, I'll stress, we don't actually have any ground truth for the robot trajectory. So we're doing all of this in a somewhat self-supervised setup. We're just using the data itself to learn. Not sure what happened there. I'm going to skip the simple examples and just do the one that's really more interesting, so I have time to wrap up at the end. So this is the third example, the lidar odometry. We've got a deep neural network that's extracting point landmarks from dense 3D point clouds, and we're outputting not just the locations of these landmarks, but also some form of covariance. So we've parameterized a covariance. We then feed that into our classic, now exactly sparse Gaussian variational inference solver. So we can actually estimate the locations of the landmarks. And all of this is now linked end to end. So what we can do is when we hold the latent trajectory fixed, or the distribution for it, we can back propagate all the way back through the neural network in a single framework, which is actually quite useful. To give you a sense of what this looks like, here's just training and testing on a few examples from the Kitty dataset. So blue is what happens when we initialize the network with random weights. So we see we do a very bad job of doing odometry in this case. And fully unsupervised, meaning with no ground truth, we're able to alternate through this expectation maximization framework and optimize the weights for the network in order to do well on this odometry task with no ground truth. And the result is the red trajectories. So on the left, we have training, and on the right, we have testing. And we can see that in this case, we're just doing frame-to-frame odometry. We're actually doing pretty much close to state-of-the-art for what frame-to-frame odometry would look like. Most of the really good methods out there use multiple frames, more than 2 frames at a time. So that's what we're going to look at next. You can actually introspect into the network and see sort of what it pays attention to, different types of features like vertical, horizontal, or even features at the interface of vertical and horizontal, which is kind of a nice property. Okay, so trying to wrap up, I see I'm just 1 minute over time. We kind of feel like this framework is a useful thing to let us start from a single loss function and exploit the sparsity of our graphical model as an inductive bias for learning, hopefully in an end-to-end fashion. And we really like that this connects our models at the mathematical level. So we think it's kind of a clean framework to do system ID, calibration, feature learning all together. And it lets us assemble different tools for the different parts of our problem and still link them. Maybe starting from a single loss function opens the door to providing specifications at the system level, because we could add constraints or other terms on the loss. And if we can do that, does that mean we can sort of build, if we can start from a single loss function, can we sort of build some form of autonomy template for different problems? So I'll talk more about that on just the next slide. We do need to get our performance up on more real problems. We want to use more random variables and less parameters so that we can actually keep track of uncertainties in our models, and that's possible in this framework. Try things with more rich sensors, different robot bases, scale up to the full visual path following problem that I motivated the talk with, and get into templates. So this is the Mr. Potato Head challenge that I wanted to mention at the end. So the idea with this is take any rich sensor, like a radar, a lidar, a camera, attach it to any robot base, drive around, get a training set of input-output data, and then try to just sort of auto-generate something like a visual path following algorithm. And the idea would be that from the data set, you can fill in all of the necessary details of the algorithm without having to sort of manually build all these different things like calibration, feature design, all of those. So, sorry, I'm 2 minutes over. this is just the last slide. I'm happy to take any questions. We hope this framework will let us be able to auto-generate some form of visual path flowing that will do something almost as good as this, which we designed completely by hand and took multiple years of work. So we'll see if that comes true. I'll take any questions you have.
All right, wonderful. Thank you so much, Tim, for such a great talk. So we seem to have a couple of questions in the chat. So the first one from David is, could you briefly comment a bit on the difference between variational inference with your method relative to the popular ISAM approaches?
Yeah, so ISAM, they're orthogonal concepts, I would say. So ISAM is exploiting sparsity to build up a really nice incremental solution, but they're still using maximum a posteriori inference in the back end, which is to say that they're trying to come up with the best state, the most likely state from the posterior, and then they use a Laplace approximation for the uncertainty. What we're doing inherently is optimizing the mean and the covariance of the unknown distribution together, which is different than just doing the mean and trying to post hoc come up with the covariance after the fact. So you could actually use this within ISAM.
Great. We have another question from Mao Ling Gao asking, how fast is the variational inference? I guess it's slower than second order methods popular in the localization problem, such as Levenberg, Marquardt, because it does more than just a point estimation. Can you comment a bit on that? And then there's a follow-up.
Yeah, it's a great question. The detailed answer is in that IJRR paper that's up on arXiv. It is more expensive. There's two-part answer to the question. From a state size point of view, our complexity is the same. So if it was a straight up trajectory estimation problem with no landmarks, it would be linear in the number of time steps, for example. So this is still linear in the number of time steps, but the coefficient is going to be higher because we're actually using samples to evaluate these expectations on the right-hand side, whereas you can think of maximum a posteriori as just using one sample, whereas we have to use multiple samples to compute these expectations on the right-hand side. There's a couple of tricks in the IJRR paper to get it a little bit faster, so something more like a Gauss-Newton version of the algorithm that's a little bit faster and doesn't need as many samples, but yes, it's an issue. However, you could actually use this in the offline parameter learning part so that you've got the best tool for building the uncertainty models, and then still go back to maximum a posteriori online.
Great. Let's see, we have a question from Ransalu who's asking, I assume mean field variational inference is what you're using here. When using the mean field approximation, what are the practical aspects that we should consider when decomposing the approximate posterior?
Yeah, so we're not actually doing a mean field assumption on the variational estimate. So we're keeping, the only assumption we make on the variational estimate is that it's Gaussian. So we're keeping all of the correlations between all of the variables. So mean field would assume that all of the variables that you're estimating are independent of one another. We don't make that assumption.
All right, great. So there are a couple of other questions in the chat, but Tim, maybe if you can stick around for a little bit, perhaps you can respond to them there directly, and we can move on to our next chat. Our next talk.
Sounds good. Thanks a lot.
All right. It is my pleasure to introduce our next speaker, Professor Aaron Ames. Aaron is the Brand Professor of Mechanical and Civil Engineering and Control and Dynamical Systems at Caltech. Prior to joining Caltech, Aaron was an Associate Professor in Mechanical Engineering and ECE at Georgia Tech. Aaron and I share the same alma mater, UC Berkeley. He received his PhD in Electrical Engineering and Computer Science from UC Berkeley in 2006. after which he was a postdoc at Caltech, and after which he joined as an assistant professor at Texas A&M University in 2008. Aaron has won several awards, including Leonard Chua Award at UC Berkeley, the NSF Career Award, the Donald P. Ekman Award for his outstanding contributions to automatic control and nonlinear science. Aaron's research interests span across areas of robotics, nonlinear control, and hybrid systems, with a special focus on application to bipedal robotic working, both formally and through experimental validations. His lab designs, builds, and tests novel bipedal robots, humanoids, and prostheses with the goal of achieving human-like bipedal robotic locomotion and translating these capabilities to robotic assistive devices. Welcome, Aaron, and we are very excited about your talk.
Thank you. Thanks for the great introduction, and thank you for hosting a fantastic workshop. It's been awesome seeing all the different perspectives on autonomy, so hopefully I can add a little bit more to that today. So with that being said, before beginning, it's of course necessary to thank all the students and collaborators that made this happen. All the videos you see here are, of course, a result of their hard work, not mine, but I get to talk about it, so for that I'm very thankful. All right, so with that being said, I think we've established throughout this workshop and in general that autonomy is going to be really, really hard. So this is not autonomy, this is just trying to get a robot to run, and that alone is hard. And now you can imagine trying to put this running robot in an autonomous situation where it has to walk outside or operate in uncertain environments, and all of a sudden the challenges get even more massive. So that being said, though, once you finally get those pieces together, it's really pretty. So this is kind of where we want to get on the autonomy level, is taking all these fragments that we have across all the different layers of the architecture and bring them together into this simple, beautiful sort of combination of things. But in doing so, we really want to be sensitive to safety. So that's kind of the tenor of this talk. And the idea of safety is we want our system to do the right thing all the time, irrespective of uncertainties, again, in environment, even in gravity. So this is a video by JPL on the Mars 2020 mission with the helicopter and the rover working together. And the question is, how do we take autonomy to this level? That is, how do we take autonomy to Mars? And how do we know that it's going to work when we send things there? And that's really the challenge, because we can't, if a robot breaks, we can't just go fix it really quick on Mars. So we have to really make sure that everything is operating properly. So with that being said, here's the overview, in my mind, kind of the big picture. And this ignores a lot of layers. And we've seen a couple examples of the layered architectures that are present in autonomous systems. But at a broad level, these are kind of the components. So we have the continuous world, which is our models of what's actually happening on the robotic systems. They're models of the plant. And we have the discrete world, which is sort of where our planning layer lives, right? So we have to make decisions. And from those decisions, we need to pass those down to the dynamics and have the robot actually do something, and then bring that back up to the decision layer. So at a sort of graphical level, we have some plant. In this case, it's a Cassie robot, just as an example, with really highly nonlinear dynamics. And we want to bring these pieces together. So I'm showing one video here for the high and low level, because we really want to combine these specifications. We want the low level control, like walking, and then we want the high level control, like don't fall. We want those two things to work in tandem. So the question becomes, in an autonomy context, how do we bridge this divide? How do we unify this continuous and discrete viewpoint of the world into a single coherent framework? So I don't have an answer to this, but this talk is giving sort of one possible hint towards a solution, if you would like. So with that, we can kind of talk about the two different layers independently, and then I'm going to talk about the unification of the two. So beginning at the low level layer, that is the continuous layer, there's a lot of tools we can leverage, and I'm going to briefly summarize two of them, my sort of two favorite tools, which is Lyapunov theory and control barrier functions. So Lyapunov for stability and barrier functions for safety. So, and I'm going to show how these two are actually really the same thing in a second. All right, so beginning with Lyapunov, and we've seen a lot of this throughout, so I'm going to be really brief here. Everyone is familiar with Lyapunov, where you have your nonlinear dynamical system. Everything I'm going to do here is for the full nonlinear dynamics. I'll assume it's in affine form, so the input is appears affinely in the dynamics, but otherwise just fully nonlinear. And we have a Lyapunov function, which is basically a bowl. And what control Lyapunov functions say is if you can find an input such that the derivative decays according to this simple linear term on the right, then you're guaranteed to have exponential convergence of your Lyapunov function dynamics. And because it's a positive definite function, this implies convergence of your error dynamics. So Lyapunov, in essence, projects your high-dimensional nonlinear system down to a one-dimensional stable system, and thereby guarantees stability of the high-dimensional system. And so I always have this video. This is the State Fair coin thing, but this is the way I view Lyapunov is coins going down this little drain. And from the Lyapunov or control Lyapunov function, you get controllers. So that's, I think, the really important point here is that from this notion of stability, you get an optimization-based controller. In this case, it's a quadratic program. It's convex. And in fact, you can see here, because of the affine assumption on the dynamics, we get explicit solutions of this controller if we would like. So from the certificates, we get controllers. And from the controllers, we get certificates of our properties. So in this case, this is a theorem from a TAC paper in 2014. But the point is, once you have these Lyapunov functions, you have an entire class of controllers that stabilize the system. Hence, you have theorems, for example, in this case, that we're going to have a stable periodic orbit. Hence, we'll get stable walking on a robot, let's say. So some examples of this, just to kind of, these are just some of my favorite videos to give some context. We have Duris here walking. And this is walking due to a CLF. I won't go into the details of how we actually implemented it, but this is a CLF sort of at the theoretical core, getting multi-contact locomotion. We can also apply these ideas to quadrupeds. This is some recent work where we view quadrupeds as actually just bipeds working together, and hence we can generate gaits. And what you saw there was actually the gait generation process in about 3 seconds. So from gait to robot in about 5 seconds. So we can do it on quadrupeds. And the great thing about quadrupeds, of course, is that they're super robust. So we're starting to have fun with quadrupeds in this context. We'll just let this, it's kind of choppy, but so meaning that the quadruped can handle all these root systems and everything else. Now, going beyond quadrupeds, we've also applied this work to exoskeletons. So this is the same general math as we did on bipedal robots, but now we can apply it to an exoskeleton as viewed as a bipedal robot. And the important thing is we can put people in it. So this is actually a complete paraplegic walking dynamically with control Lyapunov function sort of base concepts at the core. So that's kind of where we're at in the context of Lyapunov theory. There we go. All right, so going back to this picture of low level versus high level, I just want to return to Cassie, and we had this theorem, and this theorem was representing a task we wanted to achieve at this low level control. And again, because of the theorem aspect of it, it's very general, as I showed with all these applications. So this is Cassie doing a bunch of different walking with the same math you saw on Duris, the same math you saw on the Exo, the same math you saw on the quadruped. So in all these cases, we get really nice, robust locomotion. We're so robust, in fact, that this single gait can get us to walk in the lab and even on slopes outside and dirt and everything else. So that's awesome. But there's a caveat here, is this robustness is a result of really careful controller design, but it's not sort of pre-planned guaranteed robustness. And because there aren't guarantees, things happen like this. So you fall. You fall when you're in an environment that you didn't plan for, right? When you didn't guarantee safety in the system. And you'll see here the robot actually handles these roots really well until it ultimately topples. And if you look really closely, it topples not because of the roots actually, but because the legs come together and they click, which causes it to destabilize. So the notion of safety now, and the fact that safety was violated, can really be understood as violating some spatial constraint in the system. And this leads to the notion of control barrier functions. So we take this idea of safety, and we're still at the low level, but now we want to understand safety as set invariance. And in particular, what this is telling us is we need something more general than Lyapunov theory. Lyapunov theory is great, and it's served us well for over 100 years, but there needs to be something a little bit more general. And this general thing we're going to leverage is control barrier functions. And specifically, we're going to want to guarantee forward set invariance. So I just want to, I can't do it justice in a 20-minute talk, but there's a lot of history here. And the history can be traced back to 1942 and Nagumu's theorem on set invariance. There was barrier certificates in the 2000s. There's a whole bunch of stuff in the middle. I would recommend that everyone look at this the survey paper we wrote last year that has a little bit more of the history involved if you want to see some of the history of set invariance. But I want to focus on control barrier functions, which is a relatively new invention. So in a nutshell, what we have here, we have our nonlinear dynamics again. We have our safe set. So we're going to be simple here in the way we define safe sets as our safe set's going to be the super level set of a function h. And this h is going to be sort of our template barrier function, if you'd like. So the question becomes, how do we guarantee forward invariance? So we ask this question, and specifically we ask this question because up to this point, up to sort of 2014, the way we understood set invariance was to look at the boundary of the set and to say, well, as long as my h dot is pointing into the set, I'm guaranteed to have forward set invariance. The problem is for controller synthesis, that's not particularly useful. Because as you go to the boundary of the set, you'll have to switch to a new controller and then switch back. And how do you decide when those switches should happen? So we asked ourselves, what are conditions that are true on the entire set that guarantee forward set invariance? And it turns out these conditions are very Lyapunov-like, except that now h can go negative and positive. So you get and the inequalities sort of flip. So this is sort of an extension of Lyapunov. These are control barrier functions. And it's a control barrier function if your derivative is lower bounded by this negative term of an extended class K infinity function of h. And the important point here is that these are necessary and sufficient conditions for set invariance. That is, you can't do any better than these conditions, much like Lyapunov is for stability. And what that means is these are the least restrictive possible conditions on the input u that will guarantee you have forward set invariance. Hence, it gives you the widest class of controllers to leverage to get that forward invariance. And that's where the synthesis part comes in. So there was a talk earlier on barrier functions for drones, which was really nice in the real world. But the basic idea is barrier functions lead to safety filters, if you'd like. So what it does is it takes a nominal input and it modifies it minimally so that you're guaranteed to have safety. And the way it does this is, again, through a quadratic program, just like with Lyapunov functions. So we have this is actually an affine condition in U, and we modify our U such that we're as close as possible to some existing desired controller while satisfying our safety condition. And as with Lyapunov, you can have explicit solutions of this in the case when you have a single constraint, and then realize this as a real-time controller on the system itself. It's important to note that this is optimal, but it's only pointwise optimal. And this is an important consideration. There's a lot of planning you can do to try to get more global optimality, looking at longer time horizons, et cetera, but I don't have time to talk about that now. All right, so with this safety filter, you get behaviors like this. So at the top is what happens if you just put a PD controller on a Segway and you kick it. It was an unplanned for disturbance, hence it leaves the safe region. In this case, the safe region is staying upright, and it falls. With the safety filter, it filters that signal to guarantee that no matter what happens, this Segway stays upright, and in fact, we stay within the safe region. Okay, so one more note, really quick on the theoretical side. I think this is a really important point, is that control barrier functions also lead to stability of the set. So not only is the set invariant, but it's also stable. And what that implies is something that's while simple to prove, is, in my opinion, somewhat profound, because Lyapunov functions are actually a special case of barrier functions when your set is a point. So that really tells you that there's something more general about barrier functions in the way that they handle sets. Okay, with all that being said, some examples. So this is joint work with Magnus Egerstadt on multi-robot systems. So in this case, your desired controller is this blue line which says go straight. Of course, every robot wants to go straight, so the answer would be they'd all collide in the middle. Barrier functions say, well, go straight, but make sure you keep some distance around the agent, any agent that's in your neighborhood. And this is the ultimate result of the behavior. So you'll see they'll come together like they're supposed to, and then as soon as the barrier function's activated, they kind of stop, and then they start spinning. And again, all this is not some planned trajectory. This is just a result of the reactive control with the barrier functions. Another example on multi-robot systems with drones. In this case, a human's flying one drone and the other drones are flying on autopilot. And again, same general behavior where the barrier function is preventing these drones from hitting one another. And I'm going to be fast here because I'm limited on time, but this has been applied to automotive systems, adaptive cruise control, lane keeping. In this case, this is a lane keeping example where the human's trying to drive the car out of the lane. This is actually done by my postdoc, Yu Shao in Michigan. This is not California, as I'm sure you would guess. And the barrier functions preventing the car from leaving the lane. We've done it on boats. So in this case, the barrier functions prevents the boat from hitting the dock. So safety features on boats, you'll see that it starts to brake. This braking is based on the barrier function while the human tries to drive it into the dock. We've also done it on exoskeletons. So in this case, the barrier function keeps trajectories within a tube. And the U desired is the human trying to walk with the exo. So the human's trying to walk naturally, and the barrier function is ensuring that the behavior is actually safe. We've done this on a bunch of clinical testing. So that was really fast, but I want to get to the final part of the talk, which is starting to bring together the high-level control into this low-level, because everything I've talked about to date has been continuous dynamics, low-level control. So the question is, how do we bring this together with this discrete level? So let me talk about the discrete level. Again, this will be somewhat high level, but I want to just communicate the point. So there's a bunch of methods out there to do discrete level sort of planning in a provably correct way. Some of the most popular are Markov decision processes and PalmDPs. We saw examples of that throughout this workshop. You know, at the MDP level, we've applied these kind of concepts, for example, to this original example I showed you. So in this case, what happens is you have a MDP, which is transitioning between these different domains where you have sort of explore and plan. And so the rover in this case goes out, it can't find a path, so it sends out the UAV, in this case a drone, which then explores the environment, records that information, passes that back down to the rover, and the rover finds a path to go on and it can get to the desired destination. So this is nice, but I'm being brief here because the reality is what we saw in doing this is how fragile it was. So this was the opposite of robust, in that we had to run this trial like 1,000 times till we finally got the one that worked in that video you saw. And what kept happening is all these errors. In this case, you'd see the motion capture started to fail, and hence the controller went bonkers. This is another example of motion capture failure. So the question is, how do we bring this final piece together, which is safety critical aspect to the plan? So we've recently done work on this with my postdoc Reza, and the idea is the following. We're going to now go to PalmDPs. And in the PalmDB context, this is what we're going to do. We're going to leverage barrier functions like we did for the continuous dynamics, but now at a discrete level. So in particular, let's consider this multi-robot system, consisting of multiple robots that have heterogeneous capabilities. And the nice thing about PalmDPs is you can take a PalmDP and get to it a discrete time dynamical system on the beliefs. So this is the dynamical system you end up with based on the PalmDP description. And once you have that, you can start to talk about barrier functions, except now they're going to be at the discrete time level. So we can take this discrete dynamical system, look at this barrier function condition, and in fact, we get necessary and sufficient conditions for set invariance for this discrete time dynamical system, just like we had for the continuous dynamical system. But now this can be applied to the PalmDP and the discrete time dynamical system you get from the PalmDP. The great thing about the discrete perspective is you can do a little more than you can do with continuous systems. What I mean is you can start to consider more complicated sort of specifications, as was seen in this workshop. When you're at this PalmDP level, you can start to talk about temporal logics and everything else. So this is a specific example where we're taking intersection and union of sets. So we have a bunch of safe sets defined by different barrier functions. This is on the discrete time dynamics. And we can intersect and union these sets, and we get corresponding conditions on the barrier functions for the intersection and the union. So that's a simple example of a specification, but we can take these ideas even further. And in fact, we can consider distribution temporal logic and look at all the corresponding specifications. And for these specifications, we can have barrier function instantiations of the specifications. So we can take any existing action that you might have planned for your PalmDP, and we can minimally modify that sequence of actions so we can guarantee safety. And this is just a quick graph of what it looks like. So the nominal policy violated safety almost the whole time. It went below that red line. And we can modify it minimally to guarantee safe action subject to a specification. So this is just illustrating that we can start to think about the planning side in a safety critical way, right? So this is a video kind of demonstrating these ideas where we have these multiple agents and they all want to leverage their own capabilities. So you first have the quadruped that goes out and finds the target because it's the most capable. Then you have the trackbot, which goes next. And finally, the rover or the Segway, which goes last. And of course, right now, this is all at the planning level. What we want to do is integrate this with all the safety critical control at every previous level like I presented. So that's these ideas coming together. And we hope to do this not only on these somewhat statically stable systems. I guess the Segway is dynamically stable and so is the quadruped, but we hope to also incorporate bipedal robots together with quadrupeds in this autonomous planning environment. Again, we're at the embedded and the real-time control level. We have all the safety guarantees baked in that I talked about earlier with barrier functions for those. So we have layers of safety critical control through the entire hierarchy of autonomy. So by the way, this, just to be clear, this is not autonomous at all. This is 2 graduate students just playing with the robots. That's why it says next steps. This is the kind of stuff we'd like to do autonomously. And we'd like to also understand this interaction, this autonomous interaction. So that's my viewpoint on autonomy in 20 minutes or less. The idea is to kind of attack this entire hierarchy and find unified mathematical principles across the entire hierarchy. If it's okay with the organizers, just a couple thoughts going forward, since I'm at time. Good, okay. So just a couple things on what's next. Again, very high level, but I just want to talk about it. There's a whole bunch of different application domains we can consider. We've already seen these, from robotic systems, safety critical to robotic assistance. So a couple examples of this, and these are things that were actually touched on today in different aspects, so I just want to kind of mention it. We could talk about bringing learning into the picture. So we have some recent work on doing learning with control barrier functions, where we're trying to identify sort of the unknown dynamics in the system. We learn these at the level of the barrier function to guarantee safe behavior. So this is what's being done experimentally on board the Segway to guarantee safety. We also can look at robustness. This was discussed today. So if you have uncertain model, uncertain sensing, uncertain estimation, how do you incorporate that into the picture? So we have some recent results where we're making sure we're robust to all that uncertainty. So the top is what you do if you just do a barrier function with the uncertainty, and the bottom is if you plan in robustness. We're looking at a whole bunch of different walking and dynamic behaviors on robotic systems. So jumping, walking quickly, walking on predefined paths. So how do we bring all these more complicated behaviors into the picture? We're starting to think, of course, about robotic assisted devices. I showed the exoskeleton earlier. We have a new ROAMS initiative at Caltech where we're able to test a lot of these ideas in more detail. 2 quick examples of this. We're starting to think about machine learning together with our prosthetic in the lab. So here we're doing RNNs on the prosthetic, onboard control. So we're running the RNNs in real time on the prosthetic to learn the complicated controllers that we're running. We're also doing learning on the exoskeleton. So in this case, it's preference-based learning. So we're learning impact or input based on the user preference to try to find the ideal or optimal gait for the user based on a motion library of gaits. So these were just a smattering of examples of the kind of directions we're heading. And to bring it all together and closing, the ultimate goal is to do stuff like this. Of course, this was my graduate student driving the robot, but this is where we really want to be. We want to be with autonomous systems like walking robots out in the real world, interacting with people in dynamic and interesting ways, to ultimately in a robust fashion, which is the whole point of this workshop. And I think this is really the critical point. Without robustness, we will never get to robots in the real world. So hopefully this talk gave a couple ideas of where my thoughts are on the subject. And with that, thank you very much for listening. Thank you.
Thank you, Aaron, for a wonderful talk and great visuals. There are a couple of exciting questions in the chat box. So hopefully we can go through some of them if you still have a few minutes. So one question is around kind of numerical issues associated with control barrier functions. So do you encounter any numerical or sampling time issues when you using control barrier function for safety critical systems, particularly near the boundary of the constraint?
Particularly what?
Near the boundary of the constraint.
Yeah, so then yes, absolutely. Numerics are very important. So, you know, if you have a continuous time representation of your system and you're doing the barrier function, when you go to discrete time and real world implementation, the numerics will be absolutely be an issue if you're not careful. There's a couple places where this shows up. First is these, the QPs you get are continuous, Lipschitz continuous, specifically if you have a valid relative degree for your barrier function, but they're not smooth. And continuous but not smooth controllers on hardware can result in sort of weird kind of oscillating and chattering when you discretize it. So that's one point, and that chattering can actually result in you leaving the boundary. There's other issues related to discretization and the implementation on hardware. So yeah, this is absolutely an issue. There's a couple ways to kind of deal with this. The more sort of the easier way is to just kind of buffer your safe sets, right, based on sort of your sampling time and everything like that. Of course, that's a hacky way. We have a recent paper where we did event-triggered control with control barrier functions that just appeared in CSL. So that's the better way to handle it. And we gave conditions. And again, that also involved kind of buffering your sets a little bit. But we're able to actually determine what the update rate should be on your controller to guarantee safety as you discretize and implement sort of in real-world environments. So you check that out as an example of how to handle that gap between the continuous and discrete dynamics.
Great. Thank you, Aaron. Another question is around the feasibility of the safety controller. So can you talk a little bit about how to ensure that the safety critical controller program is feasible? Does that follow from the set invariance of control barrier functions?
Yeah, so that's a great question too. And I again, there's a lot of theory under the hood here that I can't do justice to in 20 minutes. So I recommend reading some of the papers that I link throughout. But in terms of feasibility, so if you have a valid relative degree on your barrier function, it will always be feasible as a QP, as I presented it, assuming unbounded torque. So when you start to have input constraints, then all of a sudden you're going to have kind of a feasibility problem potentially, right? That is, your derivative condition might require more torque than you can provide to the system itself. So the only way to really guarantee feasibility is to come up with a control invariant set. So that will guarantee feasibility over all possible inputs. Or, for example, you can use Hamilton-Jacobi equations, right? Or you can program it up using SOS. So there's lots of ways you can kind of use existing methods. Of course, all of those are computationally expensive. We have some recent stuff as well where we use sort of trajectories and a backup set to make sure we're always feasible. So this is an open problem, I'll say, at a broad level, where if you want to guarantee feasibility subject to real physical constraints on the system, then you have to be careful with how you design your barrier function. And this is something that you have to really pay attention to.
And you touched upon this a little bit, but on the one question is around the role of learning in the autonomy pipeline that you outlined in your talk. So it touches upon that, but like, where do you see the broad roles of learning going forward?
Yeah, so that's a good question. Again, it has a long answer. I'll try to be brief though. So there's a bunch of ways in which you can do learning, and you know, the hierarchy I showed, you can do learning at these different levels. So for example, we did preference-based learning. That's sort of at the planning level, if you'd like, what gate to select. And in that case, you can do it safely by making sure that any choice you make would be safe, right? On the other hand, if you have a learning loop, like let's say you have a camera system and you want that in your autonomy loop, then you can, for example, filter that through the barrier function and use the barrier function as a filter for the learning. On the other hand, if you're actually doing online learning and you want to make sure it's safe, there's actually some nice work on doing, for example, RL with barrier functions to make sure you're exploring safe regions. And of course, finally, there's uncertainty in the system, and you can talk about learning that residual dynamics, that uncertain dynamics, both in the context of barriers and just in general. So I would say the learning question is a very good one. I think at a broad level, learning apps in some way, shape, or form, or adaptive control has to be part of the picture because there will always be uncertainty. But I think the hierarchies and where you do the learning and how is really the critical question to ask in an autonomy context. And making sure you do it in an intelligent and layered way so that you mitigate any issues that the learning has in terms of you know, sort of bounds it may give you in the process. That might be a little bit of an unsatisfying question, but that's no, it's an interesting, I mean, this is still really an open problem that's just beginning to be explored.
Cool. And then there are some more questions in the chat box, but in the interest of time, if you can stick around for a little bit longer and answer those questions, that would be wonderful. Sure. And thank you again for a wonderful talk.
Thanks for having me. Thank you for a wonderful workshop.
I will now hand over to Andrea, who has some closing remarks for us. So Andrea, whenever you are ready.
Yeah, thank you so much, Aaron, and thank you to all of our speakers, both in the first section of our talks as well as more recently. I have a few things to share. So as we were watching all these invited talks today, I just wanted to quickly summarize some of the key takeaways that at least I think the organizers, we took away. I'm sure there's many more. But just to start off, so in Katie's talk, we saw the value of how simulation can really help us identify these corner cases about situations that we might need to safeguard against in the real world. We saw Tom talk about how we can actually leverage a lot of tools from statistics and machine learning for anomaly detection. Ram gave us some great insights into how to design robust motion planners for real-world robots. We saw from Tim how one loss function can really help us easily build these autonomy templates and reduce manual design. And from Aaron, we just saw how we can really use control barrier functions to augment control intelligently and preserve safety for real robots like the Cassie. There are a few other things that came up too while we were listening to these talks, and these are sort of maybe like nuggets or food for thought for all of us to take away from this workshop. So the first is, I think there was a great question that was posed by Hadass, which is how do we develop the right simulation models for complex real world environments, whether these be simulating people around us or other autonomous vehicles or simulating perception pipelines, like how an actual camera works properly. So these are really difficult things that a lot of us need to be considering when we're talking about robustness and talking about failure detection. Another thing to consider in light of Tom's talk was how do we classify the types of anomalies and also automatically generate safe behaviors for autonomous systems in response. So if a system is doing some kind of anomaly detection, what should it do once it detects an anomaly? From Ram, we saw some great stuff on scaling up these robust planning techniques, but there's always more to do. So how do we scale up and make these safe, robust planning techniques work in real time? I really liked Tim's Mr. Potato Head challenge. That was a fantastic sort of question to pose for the community. So if you take a rich sensor, attach it to your robot, get that training set, and try to auto-generate a visual path following algorithm from just the data set without manual design, I think that's a great question and test sort of how far we can push our autonomous systems to truly be autonomous just given some training data and a sensor. And finally, Aaron, I think, concluded with a great high-level question, which is how do we robustly unify these discrete high-level reasoning tools like MDPs, POMDPs with all of the knowledge we have about continuous dynamics and continuous control when we're actually designing real-world robots. So finally, thank you to everyone who participated in the workshop as a speaker and also just as an attendant. Please tune in to our workshop website. Later, we will post this full recording. And thanks so much again for everyone's participation. We really enjoyed it.